The glass of water on the table. The floor beneath your feet. The quiet air in the room. They feel solid. They feel real. A lifetime of experience tells us they exist, whether we are looking at them or not. It's the calm foundation upon which we build our lives, the idea of a definite, independent reality that we are simply moving through. Welcome to the science for deep sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. But what if, deep beneath this solid world, that foundation is not as firm as it seems? What if the fabric of everything is not a fixed thing, but a shimmering field of possibility? What if that glass of water, that chair, and everything you perceive as concrete only settled into place because you observed it? This is not a thought from a dream. This is the quiet and profound implication at the heart of quantum mechanics, the most carefully tested understanding of the world in human history. It suggests that our perception of a stable, classical world might be a beautiful illusion, and that reality, at its most fundamental level, is something we participate in. Today, we journey into this quiet, uncertain realm to ask one of the deepest questions there is. What is reality, and what is our part in it? The world you thought you knew. Before we enter the quantum world, it's helpful to remember the world it replaced. For centuries, our picture of the universe was shaped by what we now call classical physics. This is the physics of Isaac Newton, of planets in their orbits and apples falling from trees. It is a world of comforting predictability. In the classical view, everything has definite properties. A ball has a precise location and a precise momentum at all times. If you know those properties, you can, in theory, map out its entire future. This idea was perhaps best captured in a thought experiment from the 19th century scholar Pierre-Simon Laplace. He imagined a vast intelligence that could know the exact position and momentum of every atom in the universe at a single moment. For such an intelligence, he argued, nothing would be uncertain. The future, like the past, would be present before its eyes. The universe, in this view, is like a magnificent clockwork mechanism. Once set in motion, its future is written. Every event, from the collision of galaxies to a thought in your mind, is just the unfolding of a story that has already been decided. This clockwork universe feels intuitive. It matches our daily experience. Objects are reliable. They have properties that exist without us. A tree in a forest has a definite shape and size, even when no one is there to see it. Our role as observers, in this picture, is passive. We are an audience watching a film that has already been made. We can witness the story, but we cannot change it. Reality is, out there, separate from the mind that sees it. For more than 200 years, this idea was the bedrock of science. It gave us the Industrial Revolution and let us build the modern world. It seemed that the fundamental rules of the universe had been found. But as the 19th century gave way to the 20th, scientists began to look at the very small, the world of atoms and the particles within them. And it was there, in the quiet foundations of our world, that the beautiful, orderly clockwork began to fade. They found a world that was not determined, but probabilistic. A world where a particle could be in many places at once. A world where the simple act of looking at something changed what was there. The comfortable dream of a clockwork reality was ending, and a much stranger picture of existence was starting to emerge. The first quiet clue, the double-slit experiment. The first, and perhaps most famous, clue to this deeper reality came from a simple experiment, the double-slit experiment. It is a quiet gateway into the quantum world, and it remains one of the most elegant demonstrations of how reality works in ways we do not expect. To understand it, let's first imagine how it should work based on our everyday world. Imagine a wall with two thin, parallel slits in it. On one side, a machine fires tiny marbles, one by one, toward the wall. On the other side is a screen that shows where each marble lands. Over time, the screen will show two distinct bands, lined up with the two slits. This makes sense. Each marble is a solid object that follows a single path. It goes through the left slit or the right slit, and lands on the screen. There are no surprises here. Now, let's change the experiment. Instead of marbles, we send waves across a tank of water. As the waves pass through the two slits, they spread out and interfere with each other. Where two crests meet, they make a bigger wave. Where a crest meets a trough, they cancel out. The result on the screen is not two bands, but an interference pattern, many stripes of high and low intensity. This also makes perfect sense for waves. So, we have two clear results. Particles make two bands, and waves make an interference pattern. Now, let's do the experiment with electrons, the tiny particles that are the building blocks of matter. An electron is a particle, a tiny bit of stuff. So, if we fire them one by one at the two slits, we should expect to see two bands, just like the marbles. And yet, that is not what was found. When this experiment was first done, something astonishing happened. Even when firing the electrons one at a time, so that each one travels alone, the pattern that builds up over time is an interference pattern. It's as if each electron, by itself, passed through both slits at once, behaving like a wave and interfering with itself. This result is so unfamiliar, it's worth pausing on. How can a single particle be in two places at the same time? Our intuition says this is not possible. An object is either here or it is there. So, physicists decided to peek and see which slit each electron actually went through by placing a detector near the slits. And this is where reality showed itself to be even quieter and stranger. The moment they turned on the detector to watch the electrons, the interference pattern vanished. The electrons, as if aware they were being measured, stopped behaving like waves. They started behaving like particles again. The pattern that formed on the screen was just two simple bands, exactly like the marbles. When you don't look, an electron goes through both slits. When you look, it goes through only one. This is often called the observer effect. But it's important to understand what observation means here. It does not require a conscious person. In quantum mechanics, an observation is any physical interaction that extracts information. An automated detector, a single photon of light bouncing off the electron. Any interaction, no matter how subtle, is a form of measurement. This interaction is what changes the outcome. The universe, it seems, behaves differently when it is not being measured. Properties we assume are fixed, like the path of a particle, appear to be undefined until an interaction makes them definite. The double-slit experiment is the first quiet piece of evidence that our classical view of the world is incomplete. It shows that at the smallest scales, particles don't have definite properties like position until they are measured. Instead, they exist in a state of multiple possibilities, described by a wave of probability. This wave function isn't a physical wave, but a mathematical description of all the potential realities of the particle. The act of measurement causes this wave of possibilities to collapse, and only one outcome becomes actual. The world at its foundation is not a collection of things, but a collection of possibilities. And the bridge between possibility and what is actual seems to be the act of measurement itself. A field of possibilities, superposition and the wave function. The double-slit experiment asks us to accept a concept at the very center of quantum mechanics: superposition. In our world, things are definite. A coin lands as either heads or tails. A light is either on or off. Superposition is the quantum equivalent of being both at once. Before a measurement is made, a quantum system like an electron doesn't have a single, defined property. Instead, it exists in a quiet, probabilistic blend of all its possible states simultaneously. The electron in the experiment isn't going through the left slit or the right slit. It is in a superposition of going through the left slit and the right slit. A radioactive atom isn't just waiting to decay, it exists in a superposition of being both decayed and not yet decayed. It is not that we just don't know which state it's in, the state itself is indefinite. The particle's reality is spread out across all possibilities, described by what is known as the wave function. The wave function is the central mathematical tool of quantum mechanics. You can think of it as a wave of possibility. It describes the likelihood of finding a particle at any particular location if you were to make a measurement. Where the wave is high, the probability is high. Where it is low, the probability is low. But until the measurement happens, all these possibilities coexist. The particle is not a point, but a smeared-out cloud of potential. This idea is so different from our experience that one of the founders of quantum theory, Erwin Schrödinger, created a famous thought experiment to show how strange it seems when applied to our world. This is the story of Schrödinger's cat. Imagine a cat inside a sealed box. With the cat is a single radioactive atom, which is in a superposition of having decayed and not decayed. This atom is connected to a detector, which, if it senses decay, will trigger a hammer to break a vial of poison. Now, the box is closed. According to quantum mechanics, the atom is both decayed and not decayed. Therefore, the detector is both triggered and not triggered. And so, the cat itself must be in a superposition of being both dead and alive. According to the math, the cat is not in an unknown state, but an indefinite one. It is a blend of a living cat and a dead cat. It is only when we open the box, when our act of looking interacts with the system, that the wave function collapses. In that instant, one reality is chosen. We find the cat either definitively alive or definitively dead. Schrödinger meant this as a way of showing the strangeness of applying quantum rules to large objects. And yet, for 100 years, experiments have confirmed that superposition is real. In recent years, scientists have placed larger and larger objects into this state. For instance, researchers have demonstrated quantum interference with massive nanoparticles, composed of thousands of atoms and about the size of a small virus. These objects, large enough that we would expect them to behave classically, still showed the telltale wave-like nature of superposition. This tells us something profound. The strangeness of the quantum world isn't neatly confined to the subatomic realm. The boundary between the quantum world of possibilities and our classical world of definite outcomes is blurry. The universe, at its base level, appears to be a shimmering field of potential, governed by the ebb and flow of probability waves. Our solid, predictable reality is something that emerges from this underlying uncertainty. The question is, how? What is the process that turns this ghostly quantum superposition into the concrete world we experience? We've traveled from the familiar world into a place built on possibility. Things we thought were simple have become strange and beautiful. If this quiet exploration of science helps you see the world in a new way, consider liking the video and subscribing to the channel. And wherever you are right now, feel free to share a thought in the comments below. The spooky connection, entanglement. If superposition challenges our idea of an object having a single state, then quantum entanglement changes our idea of objects being separate at all. Albert Einstein famously called it spooky action at a distance, and it suggests a deep, mysterious interconnectedness to the fabric of reality. Imagine a process that creates a pair of particles with linked properties. For example, they might be created with opposite spins. Spin is a quantum property, and we can think of it as being either up or down. The key is that their combined properties must balance. So, if one particle is found to have a spin that is up, its partner must instantly have a spin that is down. Here is where it becomes strange. According to quantum mechanics, until we measure them, neither particle has a definite spin. Each is in a superposition of being both spin up and spin down. They are described by a single, shared wave function. Now, let's separate these two particles, sending them in opposite directions, across a room, a city, or even a galaxy. The moment you measure the spin of the first particle and find it to be up, you instantly know that the second particle, no matter how far away, will be down if measured. It's as if measuring one particle has instantaneously affected its distant twin. This connection seems to happen faster than the speed of light, which, according to Einstein's theory of relativity, should be impossible. Einstein and his colleagues believed this was proof that quantum mechanics was incomplete. They argued the particles must have had definite, hidden properties from the moment they were created, like a pair of gloves separated into two boxes. If you open one box and find a left-handed glove, you instantly know the other contains a right-handed one. There's nothing spooky about it. The information was there all along. However, in the 1960s, a physicist named John Bell devised a way to test this. His theorem showed that if there were hidden variables, the correlations between the measurements would have to stay below a certain limit. If the strange quantum connection was real, the correlations would exceed that limit. Over the last several decades, experiment after experiment has been performed. The results are unambiguous. The limit has been broken every single time. The universe is more connected than it seems. There are no pre-existing, hidden variables. The properties of the particles are not set until the moment of measurement, and yet their connection is real. It's important to know that this does not allow for faster than light communication. You cannot use entanglement to send a message. The outcome of your measurement is random. You can't force your particle to spin up to send a 1. You can only measure it, get a random result, and then later, by comparing notes with your friend, see that your random results were perfectly correlated. But the philosophical implications are humbling. Entanglement quietly dissolves the idea that an object is only influenced by its immediate surroundings. It shows that the universe is not a collection of separate, isolated things. At a fundamental level, it can be a single, interconnected whole. Two particles that once touched can remain part of a single system, no matter how far apart they travel. This deep connection is not just a curiosity, it is a real resource. Scientists have used it to link separate clouds of atoms, allowing them to act as a single, ultra-precise sensor for measuring things like electromagnetic fields. What we perceive as empty space does not always mean there is no connection. The world may be stitched together by these invisible, quiet threads. From weirdness to worldview, ways of understanding, the double slit, superposition, and entanglement are not theories, they are observed facts about our world. The mathematics of quantum mechanics works. It predicts the results of experiments with incredible accuracy. Where scientists differ is on the question of what it all means. What do these strange rules tell us about the nature of reality? This is where science touches philosophy. The oldest view is the Copenhagen interpretation from pioneers like Niels Bohr and Werner Heisenberg. It is a practical view. It suggests that physics should only concern itself with the results of measurements. The math allows us to predict probabilities, and that is what matters. Questions about what a particle is really doing, when we are not looking, are considered outside of science. In this view, there is a divide between the probabilistic quantum world and the definite classical world of our measuring devices. The act of measurement is what bridges that divide, causing the wave function to collapse into a single outcome. It is a useful view, but for many, it feels incomplete, leaving the question of why measurement causes this collapse unanswered. This feeling has led to other ideas. A prominent view today is based on quantum decoherence. It suggests there is no special collapse from a measurement. Instead, it points out that no quantum system is ever truly isolated. It is constantly interacting with its environment, bumping into air molecules, absorbing light. These countless tiny interactions effectively measure the system all the time, and information about the particle's state leaks out into the environment. This scrambles the neat quantum possibilities, and they fade into the background. Our classical world emerges because we are large systems, deeply entangled with our environment. We only ever see the averaged out result, not the underlying superposition. This beautifully explains why we don't see things like Schrödinger's cat in our daily lives. One related idea is quantum Darwinism. It suggests that the environment not only washes out quantum effects but actively selects for certain states. The states that are most stable are the ones that imprint many copies of themselves onto the environment. We can then learn about the system by observing just a small piece of that environment. The properties we perceive as real are the ones that have successfully spread their information into the world, creating a shared reality. Other interpretations take different paths. The many worlds interpretation takes the mathematics literally. It says the wave function never collapses. Instead, every time a quantum measurement could happen, the universe branches. In one universe, the cat is alive. In another, it is dead. You, the observer, also split. One version of you sees a living cat, and another sees a dead one. All possibilities become real, each in its own separate world. Finally, there are interpretations that bring the observer's mind back into the picture, though they remain on the philosophical edge of science. Quantum Bayesianism or cubism suggests the wave function is not a physical thing at all. Instead, it is a representation of an observer's knowledge or belief about a system. When you make a measurement, your knowledge is updated, and so your wave function collapses. An even quieter thought experiment is Wigner's friend. It imagines a scientist, the friend, inside a sealed lab who makes a measurement and sees a definite result. But for another scientist, Wigner, standing outside, the entire lab, friend included, is in a superposition until he opens the door. This leads to a gentle question. When did the result become definite? When the device measured it? When the friend's mind perceived it? Or only when Wigner himself learned of it? This has led some to wonder, quietly, if the mind that observes plays a special role. It is an idea at the very edge of what is known, a reminder of how deeply these questions touch upon our own place in the universe. Participants in the cosmos, we began with a solid, predictable world. A reality that was simply out there, separate from us. We journeyed through an experiment where looking changed the outcome. We encountered the ghostly state of existing in all possibilities at once, and the spooky connection that ties the universe together. We explored a quiet landscape of ideas, each trying to make sense of a world that is stranger than it seems. So, how does quantum physics influence our perception of reality? It quietly tells us that the world of our senses, the world of solid objects with definite properties, is an emergent one. It is a macroscopic view, built upon a foundation that is fundamentally probabilistic and interconnected. The very atoms that make up our bodies obey these strange and beautiful rules. Quantum mechanics replaces the idea of a passive observer with an active participant. At the very least, our physical interaction with the world is tied to the outcomes that become real. The mainstream view of decoherence explains this as a natural process, where information leaking into the environment solidifies reality without needing a conscious mind. But the quiet, philosophical questions remain. This leads to a humbling thought, from the physicist John Archibald Wheeler, the participatory anthropic principle. He wondered if the universe, through billions of years of evolution, might have given rise to observers, like us, in order for its own existence to become manifest. Are we, in some quiet way, the means by which the universe comes to know itself? This is not a proven fact. It is a meditation, inspired by the gentle and wondrous rules of the quantum world. What we know for sure is that reality is far more subtle and interconnected than it appears. The world is not a static stage. It is a dynamic and shimmering process. The line between us and the universe is not as clear as we once thought. We are not separate from the world we observe, We are a fundamental part of it. And as we continue to look into these deep mysteries, one thing becomes clear. The universe is not just stranger than we imagine, it is stranger than we can imagine. The observer effect is proof we live in a simulation. There is a principle in physics that suggests the world around us, the chair you are sitting on, the air you are breathing, does not possess its definite form until it is observed. It sounds like an idea from another time, a philosophical puzzle. Yet, at the heart of quantum mechanics lies a phenomenon known as the observer effect, which reveals something quietly strange about the universe. It behaves in a way that is unexpectedly familiar to computer science, much like a sophisticated program that, to conserve resources, only renders the world that is actively being witnessed. The rest of the world, vast and unseen, seems to exist only as a set of probabilities. A ghost of a world, waiting for a measurement to assign it a place. This idea suggests that the universe may not be the solid, independent reality we have always assumed it to be. Instead, it seems to respond to the act of measurement, as if our interaction is a necessary part of the code. Today, we will explore the quiet evidence that has led some to ask whether we are living not in a base reality, but inside an incredibly advanced simulation. The quantum riddle, a flaw in the foundation. For most of history, our model of the universe was stable. Reality was seen as a grand clockwork mechanism. If one could know the position and momentum of every part, the entire future of the cosmos could be predicted, and its entire past could be known. It was a deterministic world, solid and predictable. And it existed with or without us. The moon is there even when no one is looking. This classical view offered a sense of security. The ground was firm. Then, at the turn of the 20th century, physicists began to look deeper into the heart of matter, into a subatomic realm that defied everyday logic. What they discovered did not simply add a new chapter to physics, it suggested the book was written in a different language. Figures like Max Planck, Niels Bohr, and Werner Heisenberg were the pioneers of this new and unfamiliar field, quantum mechanics. They were troubled by what they found. The solid, clockwork universe dissolved into a hazy, probabilistic fog. The foundations of reality seemed to tremble. Max Planck, who originated quantum theory, once noted, "An experiment is a question which science poses to nature, and a measurement is the recording of nature's answer." In the classical world, asking a question did not change the answer. But in the quantum world, it appeared the very act of measuring fundamentally altered the answer that was given. It was as if reality changed its behavior when put under scrutiny. This idea was so counterintuitive that it began decades of debate that continue to this day. The central experiment that illuminated this strangeness is a deceptively simple one, known as the double-slit experiment. And it is here that we find the first, and perhaps most profound, flaw in our perceived foundation of reality. The physicist Richard Feynman once said that this single experiment contains the heart of quantum physics, and that, in reality, it contains the only mystery. He believed that if one could understand this experiment, one could grasp the fundamental peculiarity of the quantum world. The double-slit experiment, reality's quiet contradiction. To understand how reality seems to wait for observation, we must look at one of the most famous experiments in science. The concept is simpler than it sounds. Imagine a barrier with two small, parallel slits cut into it. On one side, a device fires particles, such as electrons, one by one. On the other side, a detector screen records where each electron lands. First, we cover one of the slits, leaving only one path open. We fire the electrons. As expected, they pass through the open slit and form a single band on the screen behind it. They behave like tiny, solid objects. If we cover that slit and open the other, we see the same result, a single band behind the second slit. So far, this is the world of classical, predictable physics. Now, we open both slits at the same time. Logic would suggest that we should see two distinct bands, a simple combination of the first two experiments. But that is not what happens. When both slits are open, the screen reveals a pattern of multiple, alternating bands of high and low intensity. This is a classic interference pattern, the kind that appears when waves overlap. In some places they reinforce each other, in others, they cancel each other out. The pattern on the screen shows the electrons are behaving like waves. There are bands where many electrons land, and areas between them where almost none land at all, places that should have been accessible. This is profoundly strange. The electrons are being fired one at a time. A single electron, traveling alone, should have nothing to interfere with. The only conclusion is that each electron, on its approach to the barrier, stops behaving like a particle. It becomes a wave of probability, passes through both slits at once, and then interferes with itself before arriving at the screen as a particle again. Let that settle. The fundamental components of reality, when unobserved, do not exist in a single place. They exist in a superposition, a quiet blend of all possible paths. The unobserved electron is not a particle but a wave of potential. It only becomes a thing in a place at the moment of impact. The idea of a solid object begins to dissolve. But it is here that the experiment becomes stranger still. What if we try to determine which slit each electron goes through? We can place a small detector next to one of the slits, designed only to register if a particle passed by. We are not trying to stop it, only to know its path. The moment we do this, the moment we observe the electron's journey, the interference pattern vanishes. We are left with two simple bands, just as we originally expected. The electrons, as if aware of being watched, stop their wave-like behavior and act as predictable particles, choosing one slit or the other, but never both. The mere act of measuring, of gaining information about the particle's path, forces it out of superposition. It collapses the wave of potential into a single, concrete reality. This is the observer effect. Reality seems to change its nature based on whether we are looking at it. Unobserved, it is a probabilistic wave. Observed, it becomes a definite particle. This is not a thought experiment. It is a result confirmed in laboratories for decades. The meaning of observation. This is the point where the mind can wander into mystical territory. The word observer naturally brings to mind a conscious human being. It is an appealing idea that our awareness is the force that solidifies the universe. A quote, often misattributed to Max Planck, states, "I regard consciousness as fundamental. I regard matter as derivative from consciousness." While the quote's origin is uncertain, the sentiment captures a popular notion. However, as tempting as this idea is, it is a misconception. The scientific consensus is clear. A conscious mind is not required. In physics, an observation is any interaction between a quantum system and its wider, classical environment, any process that records information. To know which slit an electron goes through, you must interact with it, perhaps by bouncing a particle of light off of it, or using a detector that registers a change in an electric field. This interaction is the key. According to Heisenberg's uncertainty principle, another cornerstone of quantum theory, there is a fundamental limit to what can be known about a particle. One cannot know both its precise position and its precise momentum. By interacting with the electron to learn its position, which slit it passed through, that interaction inherently disturbs the system. It is this disturbance that destroys the delicate wave-like state and forces the electron to resolve into a single path. An experiment at the Weizmann Institute of Science demonstrated this with great clarity. Researchers created a small double-slit experiment for a beam of electrons. Their observer was an electronic detector whose sensitivity could be adjusted. What they found was remarkable. The more information the detector gathered, that is, the more strongly it interacted with the electrons, the more the wave pattern degraded. At full sensitivity, the interference vanished completely. When they turned the sensitivity down, making the detector a sloppy observer that gained less information, the interference pattern began to reappear. This showed a direct, physical correlation. The amount of information extracted from the system directly influenced the reality that was measured. The observer was a machine. The act of observation is a physical process of information transfer, known as quantum decoherence. So, while we must let go of the idea that our personal consciousness is shaping reality, we are left with something that is, in its own way, even stranger. Reality is a relationship between potential and actual, and any interaction that records information is enough to collapse potential into a single, definite state. The delayed choice, a question of time. The physicist John Archibald Wheeler conceived of a thought experiment he called the delayed choice experiment. It has since been performed, and its predictions confirmed. The setup is a variation of the double-slit experiment. But this time, the choice of whether to observe the particle's path is made after it has already passed the slits, but before it reaches the detector. According to classical logic, the particle's history is already set. It either traveled through one slit or both. A later decision should not be able to affect what has already happened. In practice, this is often done with photons. A photon is sent toward a beam splitter, which acts as our two slits. The photon can take path A or path B. At the end of these paths, we can make a choice. In one setup, we allow the paths to reconverge, creating an interference pattern, the wave result. In the second setup, at the last moment, we insert another device that tells us which path the photon took, the particle result. We use a random number generator to make this choice while the photon is already in flight. The result is staggering. If we choose to detect which path the photon took, we get a particle pattern. If we choose to allow for interference, we get a wave pattern. Every time, the reality measured at the detector conforms to the choice of measurement, even though that choice was made after the photon had, in theory, already committed to being a particle or wave. It is as if our present choice reaches back and alters the history of the particle. Here, we must be precise. This does not prove that the future can change the past. The Copenhagen interpretation, a standard view in physics, would say that it is meaningless to talk about the photon's state asterisk before the measurement. It does not have a definite history until that history is measured. The entire system, photon, slits, and detector, becomes a concrete reality only at the moment of final measurement. There is no past event to change, because the event only resolves, all at once, when it is measured. Even with this more sober interpretation, the implications are profound. It dismantles our intuitive, linear sense of time. Wheeler extended this idea to a cosmic scale, imagining light from a distant quasar being bent around an intervening galaxy. The light can reach Earth via two paths. Billions of years after the light began its journey, we on Earth can choose to detect which path it took, or to see if the paths interfere. Our choice today seems to determine whether a photon traveled one path or both paths, billions of years ago. This doesn't mean we are rewriting history. It means the universe does not seem to build a concrete reality step by step. It exists in a state of unresolved potential until a measurement locks the entire story, past and present, in place. If this kind of calm exploration into the nature of reality helps you reflect, consider liking the video and subscribing to the channel. And wherever you are right now, we welcome you to share a thought in the comments below. The grand analogy, a rendered universe. Let us step back and consider what the experimental evidence has shown. We have a reality that exists as a cloud of probabilities. It resolves into a definite state only when measured. The act of extracting information seems to create the properties being measured. And this relationship is so strange that a choice in the present appears to define the state of a particle in the past. If you were to describe this system to a video game developer, they would be remarkably familiar with it. This brings us to a speculative leap. Is the universe behaving like an advanced simulation? Consider how a large, open-world video game functions. You might be standing on a virtual mountain, looking at a distant city. The world feels immense. But the game's processor is not rendering every car in that city, every pedestrian on its unseen streets. That would require an impossible amount of computational power. Instead, the game engine uses an optimization technique. It only fully renders what is in the player's line of sight. The mountain you stand on is rendered in high fidelity. The valley behind you, however, does not exist as a fully rendered environment. It exists only as data in memory. The game knows what should be there, but it does not waste resources drawing it until you turn around. The world is generated on a need-to-know basis. Now, compare this to the observer effect. The unobserved quantum world, a wave of probability, is like the unrendered part of the game world. It is a realm of pure potential. The act of measurement is like the player turning their gaze. The moment you look, the system is forced to render a definite outcome from the cloud of probabilities. Wave function collapse becomes the universe's rendering engine. This analogy provides a conceptual framework, not a proof, but a metaphor, for why reality would behave in such a non-intuitive way. In a base reality, why would the universe be so efficient? Why would it only become real when something is looking? But if reality is a simulation, this behavior is not just logical, it is a necessity. It is the most efficient way to manage finite computational resources. The observer effect ceases to be a deep mystery and becomes something more like a resource management strategy. Clues in the code, the simulation hypothesis. The idea that we live in a simulation is not new. Philosophers from Plato to Descartes have questioned the authenticity of perceived reality. But it was the philosopher Nick Bostrom who formalized the argument in 2003. He proposed that if any civilization ever develops the capacity to run ancestor simulations, they would likely create countless simulated beings. If so, a simple statistical argument suggests it is far more probable that we are one of the many simulated beings rather than one of the few in base reality. For a long time, this was a purely philosophical argument. But when viewed through this lens, several other features of our universe begin to look less like fundamental laws and more like features of a programmed reality. First, there is the pixelation of reality. Our universe appears continuous, but there is a theoretical shortest possible distance, a fundamental unit of space below which the concept of distance breaks down. It is called the Planck length. It is not zero. Could this be the pixel size of our universe? In a simulated universe, a finite resolution is not just possible, it is required. Second, there is the universal speed limit, the speed of light. Nothing can travel faster through space. In a base reality, this is a fundamental constant. But in a simulation, a maximum speed limit could be the processing speed of the computer running the simulation. Information cannot be updated faster than the processor allows. The speed of light, in this view, is the refresh rate of the universe. Third, the nature of our physical laws. The universe is, to a stunning degree, mathematical. The rules governing everything from planets to particles can be described by elegant equations. It is as if the universe is running on code. The physicist James Jeans famously said, "The universe begins to look more like a great thought than like a great machine." If our world were a simulation, its underlying structure would be mathematical code. The observer effect, a potential pixel size, a universal processing speed, and a reality built on mathematics. None of these prove we live in a simulation. But taken together, they present a consistent and provocative picture. The counter-arguments and the skeptics. As compelling as the simulation hypothesis is, it is important to approach it with scientific skepticism. This idea lives in the borderlands between physics and philosophy, and it is far from a mainstream scientific theory. The most significant counter-argument is the sheer scale of computation required. Physicists have argued that the resources needed to simulate our universe down to the quantum level would be greater than all the resources available within the universe itself. You would need a computer bigger than the universe to simulate it. However, this argument assumes the simulation would render everything, all the time. As we have discussed, the observer effect suggests a possible workaround, a system where the universe only computes what is being observed. A second objection is the problem of falsifiability. A core principle of science is that a hypothesis must be testable. It must make predictions that could, in principle, be proven false. How could we ever prove we are not in a simulation? Any evidence we find could, theoretically, be part of the program. A perfect simulation would be indistinguishable from a base reality, placing the hypothesis permanently outside the realm of science. Then there is the principle of Occam's razor. The simplest explanation is usually the best. Is it simpler to accept the strange rules of quantum mechanics as fundamental features of our universe? Or is it simpler to postulate an entirely different, more complex, base reality with beings running our universe on a computer? Most physicists would argue the former. The mainstream explanation for the observer effect is quantum decoherence, a complete physical explanation that requires no simulators. To present the observer effect as a clue to a simulation is to conflate a speculative interpretation with established science. The connection is philosophical, not yet scientific. Quantum mechanics is just strange, and perhaps that strangeness is a fundamental property of existence, not a clue that we are living inside a machine. Living in the question. We began with a simple question. What if the world only becomes real when we look at it? We journeyed into the quantum realm, where particles are also waves, and where the act of measurement seems to create the properties being measured. We saw how the double-slit experiment revealed a deep contradiction in our classical understanding of reality. From this ground of experimental science, we took a speculative leap. We saw how these quantum behaviors, this lazy rendering of reality, are eerily similar to the optimization techniques used in computer programs. This led us to the simulation hypothesis, where the observer effect is not a bug, but a feature. But we also faced the powerful counter-arguments, the immense cost, the problem of testability, and the simple fact that we may not need such an extravagant explanation. So, is the observer effect proof that we live in a simulation? No, it is not proof. It is a piece of circumstantial evidence, a glitch in our perception of a clockwork universe that opens the door to more radical possibilities. We are left where all great journeys end, with more questions than answers. We are forced to confront the possibility that the world is not the solid, objective stage we thought it was, but a participatory drama. The next time you look at the world, at the moon in the sky or your own reflection, take a moment to wonder. Are you simply observing a pre-existing reality? Or is your observation the final command that tells the universe what to be? The glitch that proves your world isn't solid. The chair you're sitting on feels solid. The screen you are looking at seems entirely real. For most of our experience, the world presents itself as a fixed and reliable stage upon which our lives unfold. But as our tools have allowed us to look deeper into the nature of matter, this intuitive picture begins to break down. At the most fundamental level, the constituents of our world do not behave like solid objects. They are not definite things. Instead, they exist as waves of pure potential. An electron in an atom does not have one specific location. It exists as a cloud of probability, a smear of existence, occupying many possible positions at once. It is, in a sense, everywhere and nowhere simultaneously. And here we find a core principle of reality that is so counterintuitive it has challenged scientists for a century. The world appears to resolve into a single, definite state only when it is observed. The act of measurement, of looking at something, seems to be the trigger that causes the universe to abandon this ambiguity and commit to one version of reality. This isn't speculation. This is the foundation of quantum mechanics, the most successful scientific theory in history. It leads us to a remarkable question. What is the nature of the world when it is not being observed? What was the universe before the first interaction that could register a state? The answer, it seems, is that it was pure potential. A silent storm of possibilities, waiting for an observer to enter the stage. The unseen blueprint of reality. For much of human history, our model of the universe was one of reassuring predictability. This was the world of Isaac Newton, a grand cosmic clockwork. In this view, planets moved in knowable orbits, objects fell with mathematical certainty, and everything from a grain of sand to a star had a definite place and a definite set of properties. Reality was simply out there, existing independently of us. An apple is red and round, whether we are in the room to see it or not. Our perception was a passive act, we were merely spectators. This classical worldview is intuitive. It is the world of our everyday lives. But at the dawn of the 20th century, as scientific instruments became powerful enough to probe the very small, researchers found phenomena that this elegant model could not account for. They peered into the atom and discovered a realm of profound strangeness that defied all classical intuition. This was the quantum realm, and our first real glimpse into its bizarre nature came from a simple experiment, one that would unravel much of what we thought we knew about existence. The double-slit experiment. Imagine a barrier with two thin, parallel slits. If you fire small, solid objects, like microscopic pellets, at this barrier, some are blocked, while others pass through one slit or the other to hit a detector screen behind it. The pattern you would expect is simple. Two distinct bands on the screen, each corresponding to one of the slits. This is the classical prediction. Now, let us run this experiment with the fundamental particles of our world, like electrons. An electron is, as far as we know, a fundamental particle, a single point. Firing them one by one, you would expect the same result as the pellets, two distinct bands. But that is not what happens. As the electrons impact the screen one by one, a completely different pattern begins to emerge. Instead of two bands, a series of multiple, alternating bands of high and low intensity appears. This is an interference pattern. It is the exact pattern you would get if you sent a wave, like a water wave, through both slits. As the wave passes, the two new wavefronts interfere with each other, crests reinforcing each other to create high intensity, and crests meeting troughs to cancel each other out. But how can this be? We are firing single, individual electrons. They are particles. They should go through one slit or the other. How can a single electron, traveling alone, create a pattern that requires something to go through both slits at once and interfere with itself? The only logical conclusion is that the electron does not travel as a simple particle. It seems to dissolve into a wave of potential, pass through both slits simultaneously, interfere with its own ghostly self, and then resolve back into a particle when it hits the screen. This experiment, first demonstrated with light by Thomas Young and later confirmed with electrons, atoms, and even massive nanoparticles composed of thousands of atoms, was the first profound sign of matter's dual nature. It is not just particles, and it is not just waves. It is somehow, impossibly, both. This wave-particle duality is not a clever trick. It is a fundamental property of our reality, and our first look into a system where the universe, at its most basic level, is not a collection of solid things, but a dynamic and probabilistic process. The glitch in the code, superposition. The double-slit experiment confronts us with a deeply counterintuitive reality. A single particle appearing to be in two places at once is a doorway into a core principle of quantum mechanics, superposition. It is here that our classical intuition is no longer a reliable guide. It is important to distinguish superposition from simple uncertainty. It is not like a spinning coin where we just don't know the outcome. In that classical case, the result is determined from the start. We just lack the information to predict it. Quantum superposition is stranger. It states that before a measurement is made, a particle does not have a definite state. It genuinely exists in a combination of all its possible states at once. The electron approaching the double slits does not go through the left slit or the right slit. It exists in a superposition of going through the left slit, A and D, going through the right slit. It is not that we don't know which path it took, it is that, in a very real sense, it took all of them. Richard Feynman's work on this idea suggests that to get from point A to point B, a particle simultaneously traverses every possible path connecting those 2 points. The mathematical object that describes this state of pure potential is the wave function. You can think of it as a literal wave of possibilities. For any particle, its wave function encodes the probability of finding it at any particular location or with any particular property. Before you look, an electron's position is not a point. Its position is the entire wave function, a probability cloud spread out over space. Its reality is this smear of potential. This is the foundational language of the universe, written not in the ink of certainty, but in the fluctuating script of probability. Reality at its most granular level is not a set of facts, but a menu of possibilities. To conceptualize this, our analogies must become stranger. The spinning coin is inadequate. A better, though still imperfect, analogy is how some advanced video games render their world. The game engine does not waste resources rendering every detail of the entire world at all times. It renders in high detail only what is necessary, what the player is looking at. Areas outside the player's view may exist in a lower resolution state, or as simple data points, until the observer turns their attention to them. Quantum mechanics suggests our universe operates on a similar, though infinitely more profound, principle. Before an interaction or measurement, a particle's properties are not definite. It is a wave function, a haze of potential. It doesn't have a definite spin. It is in a superposition of spin up and spin down. Its properties do not seem to exist in a definite state prior to being measured. They are born in the act of measurement itself. This leads to the most important question. What, exactly, forces the universe to choose? The act of creation, measurement. If the unobserved world is a realm of overlapping possibilities, then how does the solid, definite reality we experience emerge? The mechanism that transforms quantum weirdness into classical certainty is the act of measurement, and it is here that this principle becomes an act of resolution. Let us return to the double-slit experiment. We established that unobserved electrons behave like waves, creating an interference pattern. But what happens if we watch them? What if we place a detector at the slits, one that can tell us which slit each individual electron actually passes through? The moment you do this, the moment you gain information about the electron's path, the interference pattern vanishes. It is replaced by 2 distinct bands, exactly like the ones our classical pellets would have made. By observing which slit the electron went through, we appear to have forced it to behave like a particle. It is as if the electron, upon being measured, chose a single path, abandoning its wave-like nature. This phenomenon is known as wave function collapse. It describes the transition from a superposition of many possibilities to a single, actualized state upon measurement. Before the measurement, the electron's wave function passes through both slits. The moment a detector interacts with it to determine its path, this wave of possibilities collapses into a single, definite reality. One outcome is selected from the menu of probabilities. The implications are significant. The act of observation is not a passive process of gathering information about a pre-existing reality. The observation is an interaction that fundamentally influences the outcome. The choice to measure did not just tell you what the electron was doing, it appears to have determined what the electron did. This is the measurement problem, one of the deepest mysteries in physics. What counts as a measurement or an observer? Does it require a conscious being? Or simply a camera, a Geiger counter, or even a single photon bouncing off the particle? It seems any interaction with the environment that records the state of the particle is enough to collapse the wave function. This dissolves the clean line between the observer and the world. If the act of measuring something changes it, then there is no such thing as an objective, independent reality that we can passively observe. The observer and the observed are inextricably linked. We are not just spectators in a cosmic theater. We are participants, and our observations are part of the unfolding of reality itself. This is not a limitation of our instruments. Physicists have performed countless variations of this experiment. The result is always the same. As soon as you can know the path the particle took, the wave behavior vanishes. The universe seems to demand a trade-off. You can either know the path, or you can witness the wave-like superposition of all paths, but you can never do both at the same time. You, the observer, must choose which reality to bring into being. The participatory universe, the philosophical fallout. This blurring of the line between observer and reality led one of the 20th century's most brilliant physicists, John Archibald Wheeler, to a fascinating conclusion. Wheeler, who worked with Einstein and mentored Richard Feynman, was not given to idle speculation. After a lifetime grappling with quantum mechanics, he proposed an idea that challenges our common-sense view of time and reality. We live in what he called a participatory universe. Wheeler argued that the universe is not a pre-existing machine we simply inhabit. Instead, he suggested that it is brought into being, in a strange sense, by the very act of observation. No elementary phenomenon is a phenomenon until it is an observed phenomenon, he stated. To Wheeler, information was not just something we used to describe reality. Information was reality. To illustrate this, Wheeler devised a thought experiment known as the delayed choice experiment. Imagine the double-slit experiment on a galactic scale. Light from a distant quasar travels for billions of years, its path bent by an intervening galaxy. This gravitational lens creates two possible paths for the light to take to reach our telescopes on Earth, serving as a cosmic double slit. Here on Earth, billions of years after the light has already passed the galaxy, we have a choice. We can set up our telescope to see which path the photon took, like putting a detector at the slits. If we do this, we find it traveled one definite path. Or, we can set up our telescope to recombine the light from both paths to look for an interference pattern. If we do that, we find an interference pattern, which implies the photon must have traveled both paths simultaneously. The crux of the delayed choice is this. Our decision, made in the present, appears to determine the path the photon took billions of years ago. This does not mean we are changing the past. It suggests something far stranger. That the photon's past was never a definite reality to begin with. It remained in a state of superposition, an unwritten history for eons. Its story, did it travel left, or right, or both, was not set in stone. It waited for an observer, billions of years later, to ask a question. The question we choose to ask in the present moment seems to be what brings a definite history for that photon into being. Wheeler liked to use an analogy of a game of 20 questions, where the players have not agreed on a word beforehand. The guesser asks, "Is it an animal?" The first player, to be consistent, says, "Yes." The guesser asks, "Does it live in the water?" The next person, constrained by the previous, "Yes," says, "No." With each question, the set of possible words shrinks until the guesser asks, "Is it a dog?" And the final respondent, forced into a corner by all previous answers, must say, "Yes." The word, dog, did not exist at the start. It was brought into existence by the series of questions asked. This, Wheeler argued, is how the universe works. Reality is not a fixed thing. It is shaped by the questions we ask it through our experiments. If you ask a wave-like question, you get a wave-like answer. If you ask a particle-like question, you get a particle-like answer. In this view, we are not passive witnesses. We are active participants in an ongoing process that brings reality into being. Consciousness and the code. This inevitably leads to the most speculative question of all. What, or who, qualifies as an observer? For most working physicists, the answer is pragmatic. An observation is any interaction between a quantum system and a larger, macroscopic system that records a definite state. This could be a photon hitting a sensor or an air molecule bumping into a dust mote. In this view, consciousness plays no special role. The collapse of the wave function happens constantly through a process called quantum decoherence, as quantum systems interact with their environment. The universe, in this interpretation, makes itself real, without a mind to witness it. However, the sheer strangeness of the observer effect has led some, including brilliant minds, down a more radical path, one that directly considers the role of consciousness. This idea, sometimes known as the von Neumann-Wigner interpretation, proposes that the chain of quantum measurement doesn't truly terminate until it reaches the consciousness of an observer. A Geiger counter in a superposition of clicked and not clicked would remain in that state, in this view, until a conscious mind perceives a single result. Consciousness, in this interpretation, is what ultimately collapses the wave function. This is, without a doubt, a minority view in physics, and it's important to label it as such. Many find it unscientific, as it places a non-physical entity, consciousness, in a privileged position. Yet, it's an idea that persists, because it speaks to the deep connection between our inner world of experience and the outer world of reality. Its proponents were not lightweights. John von Neumann, a key mathematical architect of the theory, first formalized it, and Nobel laureate Eugene Wigner later championed it. This perspective echoes Wheeler's participatory universe but gives it a specific agent, the conscious mind. It frames the universe as a system that evolves toward producing observers, perhaps because only through an observer can the universe's potential states be collapsed into an actual, experienced reality. As Carl Sagan poetically put it, we are a way for the cosmos to know itself. A scientist studying atoms is, quite literally, a collection of atoms arranged to study itself. Whether this is true, we do not know. The measurement problem remains unsolved, and other interpretations, like the many worlds interpretation, suggest the wave function never collapses at all. All outcomes simply happen in separate, branching universes. But the idea that consciousness is fundamental provides an elegant, if unproven, solution. It suggests the relationship between mind and matter is not a one-way street. The physical world gives rise to the brain, which gives rise to the mind. But perhaps the mind, in turn, gives form and definition to the physical world. Conclusion. We began with the simple, solid reality of the chair you're sitting in. We end with a universe that, at its deepest level, behaves more like a field of probabilities than a collection of definite things. A universe where the past may not be fixed until the present observes it, and where reality itself seems to wait for a participant to give it form. The world you perceive is not a lie, but it is a high-level construction. It is a summary of a much deeper and stranger reality, one built not from solid bricks, but from bits of information and answers to questions asked by observers. The next time you look at the world, take a moment to appreciate what is happening. According to our deepest physical theory, you are not just passively receiving an image. You are participating in a fundamental act of resolution. In that moment of interaction, a universe of possibilities is narrowed down to a single actuality. You are collapsing the wave function. You are, in a very real, very strange, and very beautiful sense, making the world real. If this exploration of a participatory reality, where your observation helps to shape the very fabric of existence, has rearranged the furniture in your mind? Let us know in the comments what you think. And if you want to continue exploring the hidden structures of our reality, make sure to subscribe so you don't miss what's next. The quantum coin flip that creates your world. Everything around us feels certain. A pen, when dropped, will fall. The sun will rise in the morning. This is the world as we have always known it, governed by dependable rules. It is a reality of causes and effects, of solid objects with definite places. But this feeling of stability is a thin surface. Underneath it lies a world that operates on a different logic. A world built not on certainty, but on chance. This is not a philosophical idea. It is the world described by quantum mechanics, our most fundamental map of reality. And it tells us that the building blocks of everything we see are less like solid bricks, and more like ghostly gambles, existing in a haze of possibility until the moment they are forced to make a choice. To understand this, we do not need complex mathematics. We need only a single idea. The idea of a quantum coin. A coin that, while it is spinning, is both heads and tails at the same time. It only chooses a side when it lands, and in that moment, it creates the world you see. The two realities, a tale of a predictable world and its bizarre foundation. For most of history, the universe seemed a predictable machine. If you knew the positions and speeds of all its parts, you could, in theory, know its entire future and its entire past. This was the world of classical physics. It is the physics we learn by living. A thrown ball follows a clear arc. Planets move in orbits that can be calculated. Everything has a specific place and a specific path. This classical view was remarkably successful. It allowed us to build bridges and send probes to other planets. It was a deterministic universe. Given the same beginning, the outcome would always be the same. There was no room for ambiguity. Chance was simply a measure of our own ignorance. But toward the end of the 19th century, as scientists began to look at the world of the very small, this orderly picture began to fray. They were exploring the realm of atoms, electrons, and photons. And what they found was not just surprising. It seemed to violate the logic of the world they knew. It began with light. For a long time, there was a question. Is light a wave, or is it a stream of particles? The evidence for waves seemed overwhelming. When light is passed through two narrow slits in a barrier, it does not create two bright spots on a screen. Instead, it creates a pattern of many bright and dark stripes. This is an interference pattern, and it is a signature of waves. Waves passing through each slit interfere with one another, adding together in some places and canceling out in others. The case seemed closed. Light was a wave. But then, studies by Max Planck and Albert Einstein revealed something different. They found that light energy is not a continuous flow. It arrives in discrete packets, which Einstein called photons. This was particle-like behavior. Light was now both a wave and a particle. This was the first sign that the rules were different at the quantum scale. This wave-particle duality suggested that something could be two contradictory things at once. This strange duality was not limited to light. It was soon discovered that matter behaved in the same way. Electrons, the particles that make up atoms, also acted like waves. If you fire electrons, one by one, toward a double-slit barrier, you expect them to act like tiny bullets, creating two clusters on the screen. But this is not what happens. At first, the electrons land in seemingly random places. A dot here, a dot there. But as more and more are fired, a pattern begins to form out of the quiet chaos. It is an interference pattern. The same striped pattern that waves produce. Each electron is fired alone. There is nothing for it to interfere with. And yet, it acts as if it passed through both slits at once, interfering with itself, before landing as a single particle. It is as if the electron was aware of the entire experiment, choosing its final location based on a wave of possibility. Here, our intuition fails. It is like throwing a single ball at a wall with two openings, and having it pass through both at the same time. This experiment is the foundation of quantum mechanics. It forces us to accept a reality that is, at its core, based on probability. The wave that passes through the slits is not a physical ripple. It is a wave of probability. It describes all the possible places the electron could be found. The bright stripes are where the probability is high. The dark stripes are where it is low. So we are left with a quiet contradiction. The large world we live in is predictable and solid. But the foundation it is built upon, the quantum world, is probabilistic and uncertain. Particles do not have definite properties before they are measured. They exist in a haze of potential. This leads to a central question. How does the solid world of our experience emerge from this uncertain quantum soup? The answer is found in our analogy of the coin. It is a principle called superposition, and it is the key. The quantum coin, superposition, and the nature of possibility. To truly understand the double-slit experiment, we must look closer at this idea of being in many states at once. In the language of quantum mechanics, this is known as asterisk superposition. Let us return to the spinning coin. A classical coin, while spinning, has a state that is simply unknown to us. It is either heads or tails. Our not knowing does not change its reality. A powerful camera could capture it mid-air and reveal its state. Its state was always definite, simply hidden. A quantum coin is different. Before it is measured, while it is spinning, it is not heads or tails. It is, in a physical sense, both heads and tails at the same time. It exists in a superposition of these two states. This is not a matter of our ignorance, it is the particle's nature. It is a blend of possibilities, described by a wave function. This function holds both outcomes in a live, unresolved state. This is what happens to the electron in the double-slit experiment. Before it meets the screen, its location is not definite. It is described by a probability wave that spreads out and passes through both slits. The electron is in a superposition of having gone through the left slit and having gone through the right slit. Because it exists as this wave of potential, the two paths can interfere with each other. The electron interferes with itself. If this feels strange, it is because our minds evolved in a world of large objects. A world where things are here or there, not a smear of both. Think of a chord played on an instrument. When several notes are played together, the sound you hear is not one note or the other. It is a blend, a superposition of multiple frequencies. You hear the chord, the combination, not just the single notes. A quantum particle, before it is measured, is like that chord, a combination of all its possible states at once. In the quantum world, everything that can happen is, in a sense, happening. An undisturbed particle explores all its possible paths at the same time. The physicist Richard Feynman showed that to calculate the probability of a particle moving between 2 points, you must add up the contributions from every single path it could possibly take. Straight lines, long looping journeys, a trip to another galaxy and back again, all are part of the superposition. The paths that are simple and direct tend to reinforce one another, while the more chaotic paths tend to cancel out. This is why, in our world, objects appear to travel in straight lines. But at the quantum level, the illusion of a single path is gone. This principle applies to all particles and all their properties. An electron has a property called spin, which can be measured as up or down. Before measurement, it is in a superposition of both spin up and spin down. A radioactive atom exists in a superposition of decayed and not decayed. This is the source of the potential power of quantum computing. A classical computer bit is a 0 or a 1. A quantum bit, or qubit, is like the quantum coin. It can be a 0, a 1, or a superposition of both. With only a few hundred qubits, you could represent more states at once than there are atoms in the known universe. They explore a vast landscape of possibilities simultaneously, just as the electron explores all paths. But this brings us to a crucial part of the story. The quantum coin does not spin forever. The electron does not remain a wave of possibility. Eventually, it lands. It hits the screen. And when it does, it is a single, small dot. The chord resolves into a single note. The superposition is broken. What forces this choice? What makes the universe pick a side? This is the act of measurement, and it is perhaps the most debated aspect of all of quantum mechanics. Forcing the coin to land, the mystery of measurement. An electron, as a wave of possibility, moves through both slits at once. It exists in a superposition. But then, we look. We place a detector at one of the slits to learn which path the electron took. And the moment we do, everything changes. The interference pattern vanishes. In its place, we see two simple bands on the screen, just as we would expect from tiny bullets. Our detector at one slit will either click, telling us the electron went through there, or it will remain silent, telling us it went through the other. The act of observing its path forces it to behave like a classical particle. It takes one path, and one path only. It is as if the particle knew it was being watched. The act of observation forces it to choose. This is often called the observer effect, but the name can be misleading. It suggests a conscious mind influencing reality. In quantum mechanics, an observer does not need to be conscious. It simply needs to be an asterisk interaction. An interaction with anything. A detector. A photon of light. A single molecule of air. Any interaction that reveals which path information is enough to destroy the superposition. The moment the universe gains information about which path was taken, the superposition collapses. The spinning quantum coin is forced to land. The wave of possibility condenses into a single, concrete reality. This is the collapse of the wave function. It is the transition from the quantum world of maybe to the classical world of is. Why does interaction do this? To see an electron, you must interact with it, perhaps by bouncing a photon of light off it. That photon carries information away, but in doing so, it disturbs the electron. The act of gathering information changes the system. The quantum strangeness does not simply vanish, it leaks out into the environment, becoming entangled with the measuring device. This leads to one of the most famous thought experiments in physics, Schrödinger's cat. Erwin Schrödinger, one of the architects of quantum theory, was troubled by this idea of collapse. To show what he saw as the absurdity of applying these rules to large objects, he imagined a scenario in 1935. Imagine a cat in a sealed box. Inside with the cat is a tiny amount of radioactive material. There is a 50% chance an atom will decay within an hour. If it does, a Geiger counter detects it, releasing a hammer that breaks a vial of poison, and the cat dies. According to a strict reading of quantum mechanics, until the box is opened, the atom is in a superposition of decayed and not decayed. Because the cat's fate is tied to the atom, the cat itself must also be in a superposition. It is both alive and dead, at the same time, until the box is opened and an observation is made. Schrödinger did not believe there were zombie cats in boxes. He proposed the experiment to highlight a problem. We know that a cat is not both alive and dead. So where does the quantum description stop applying? Why can an electron be in a superposition, but a cat cannot? The answer, once again, is interaction. Schrödinger's experiment imagines a perfectly isolated box. But in the real world, perfect isolation is impossible. This is the piece that bridges the quantum and classical worlds. It is a process called decoherence. If this quiet exploration into the nature of reality is something you find valuable, consider subscribing to the channel. And feel free to share in the comments where you are watching from, and what part of this idea you find most compelling. Why your keys aren't a quantum coin, the decisive power of decoherence. Schrödinger's cat, inside its theoretical box, is a simple, isolated quantum system. But a real cat is not a single particle. It is a warm, breathing collection of trillions of cells, made of countless atoms. It is a bustling system, constantly interacting with itself and its environment. This is the key. Superposition is incredibly fragile. It can only survive in perfect isolation. The moment a quantum system interacts with its environment, its ability to be in multiple states at once leaks away. This process is called quantum decoherence. It is the silent, constant force that removes quantum behavior from the world we see. Think of the electron's probability wave as a perfect ripple in a still pond. As it passes through two slits, it creates two orderly ripples that can interfere. Decoherence is like a constant, gentle rain falling on the surface of that pond. The random interactions with the environment, the raindrops, scramble the delicate patterns. The clean ripples are lost, turning into a messy, incoherent surface. The interference pattern is gone. For a single electron in a vacuum, scientists can shield it from stray light and air molecules to preserve its superposition. But consider a set of car keys. They are not in a vacuum. They are bombarded by trillions of air molecules every moment. Photons from the lights in the room bounce off them. Each one of these small interactions is a measurement. Each one asks the keys, "Where are you?" And each time, the key's collective wave function collapses. This process is astonishingly fast. For an object the size of a dust mote in the air, the time it takes for its superposition of location to be destroyed by air molecules is around 10 to the power of minus 31 seconds. For a cat or a set of keys, the time is so short it is, for all purposes, instant. A large object is never isolated enough to sustain a superposition. It is constantly being measured by its environment. This is why we do not see cats that are both alive and dead. The cat's own warmth, its breathing, the beating of its heart, all of these are constant internal measurements. The superposition of alive and dead would decohere into a single, definite state almost instantly, long before a person could open the box. The cat, in effect, measures itself. So, the measurement problem is not really about a conscious observer. It is about the unavoidable entanglement of any system with its surroundings. The border between the quantum and classical worlds is not a sharp line. It is a gradient. The more particles an object has and the more it interacts, the faster it decoheres, and the more classical it behaves. This also explains why quantum computing is so difficult. The qubits, which must maintain their fragile superpositions, have to be shielded from the environment to an incredible degree, often in vacuums at temperatures colder than deep space. Decoherence is the constant adversary. Decoherence is not a separate theory. It is a natural result of quantum mechanics itself. It shows that the classical world is not fundamental. It is an emergent property. It surfaces from the underlying quantum reality through the constant process of environmental measurement. The solidity of a desk is a statistical illusion, born from the averaging of countless quantum possibilities, collapsed by the environment faster than we can perceive. The two worlds, one reality, the great divide of scale. We now have all the pieces. There are not two different sets of laws for the small and the large. There is only one set of laws, quantum mechanics, but its effects appear in different ways depending on the scale. At the quantum scale the world of single atoms and electrons, things are small and can be isolated. Here, wave-like behavior is dominant. Particles exist as probability waves. Superposition is the default state. An electron goes through the left slit and the right slit. This is the world of, and, a world of potential and probability. At the human scale the world of cats and keys and planets, things are made of a staggering number of particles. They are in constant interaction with their environment. Here, decoherence is absolute. Superpositions are destroyed instantly. The wave nature of matter is still there, but it is unobservable. What emerges is classical behavior. Objects have definite positions. This is the world of or. The coin is heads or tails. The cat is alive or dead. This is a world of actuality and certainty. Quantum effects do not simply turn off. They are always there, underpinning everything. The stability of atoms, the fusion that powers the sun, these are quantum phenomena. The classical world is built upon this foundation. One could, in principle, describe a thrown baseball using the equations of quantum mechanics, but the calculation would be impossibly complex, and the result would be the same as the one given by simpler, classical laws. The quantum probabilities average out to produce what looks like certainty. This is why your keys do not quantum tunnel through your desk, even though there is a non-zero probability of it happening. For that to occur, all of the trillions of atoms in your keys would have to conspire to move in the same direction at the same time, without decohering. The probability is so small, you would have to wait longer than the age of the universe to see it. It is possible in principle, but not in practice. The world feels solid because it is the result of an uncountable number of quantum coin flips, all landing and being re-flipped by the environment at every instant. The certainty we feel is the law of large numbers playing out on a cosmic scale. The world built on chance. We began in a simple, solid world. We have journeyed down into its foundations, to a place where that solidity dissolves into a fog of probability. Where particles are waves of potential, exploring all possibilities at once. We learned that this ghostly reality becomes concrete through interaction, through a process called decoherence, where the environment constantly measures every object, collapsing its cloud of possibilities into a single state. The predictable, classical world is not fundamental. It is an emergent phenomenon, a statistical consensus arrived at by a universe of ceaseless quantum coin flips. Your world is not a clockwork machine. It is more like a casino where the dice are rolled an infinite number of times every second, and the laws of probability are so powerful they produce an illusion of certainty. The chair you are sitting on feels solid, but it is a storm of quantum probabilities, momentarily frozen into a definite state by the light and air around it. The quantum coin flip is not just an analogy. It is the process. It is a continuous act of creation, the mechanism by which potential becomes actual. It is how the firm reality we know crystallizes out of a deep and fundamental uncertainty. Reality is not a static state. It is a dynamic game of chance. This leaves us with a final, quiet thought. We know that interaction with an environment is what collapses the wave function and creates our shared, classical world. But what about the universe as a whole? If the universe is, by definition, everything there is, what is its environment? What, if anything, is measuring the entire cosmos and forcing its quantum coin to land? Science proves distance is just an illusion. There is the space between you and the screen. Between the Earth and the Moon. A quiet, empty vastness that seems to define our world. But what if that separation is not as simple as it looks? What if two particles, millions of miles apart, could share a single fate? So connected that an action on one could be felt by the other, instantly. This is not a story from imagination. It is a feature of our universe called quantum entanglement. It stretches the idea of what an animal can be, suggesting that the space we perceive might be a kind of illusion. This is a journey into the quiet, strange science that revealed this hidden layer of reality. A place where, in a very real sense, everything is connected. It challenges what we think we know about space, time, and the nature of things themselves. If this kind of calm exploration into the world of science helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near a city, a forest, or somewhere quiet in between, feel free to share where you're watching or listening from. To understand this quiet strangeness, we have to travel back in time to the early 20th century. The old, comfortable world of physics, a world of clockwork precision, was beginning to unravel. In its place grew a new and unfamiliar theory, quantum mechanics. At the heart of the debate were two of the great minds of scientific history, Albert Einstein and Niels Bohr. Their disagreement was not just academic. It was a clash of philosophies about the nature of existence itself. The stage for their most famous conversations was the Solvay conferences in Brussels, gatherings where the world's leading physicists came to grapple with the new quantum reality. Imagine a room where 17 of the 29 people present were or would become Nobel laureates. And at the center were Einstein, the architect of relativity, and Bohr, whose institute in Copenhagen was the very crucible of quantum theory. The new mechanics proposed a universe that was fundamentally fuzzy. It claimed that particles did not have definite properties, like a specific position, until they were measured. Before that moment, they existed in a haze of possibilities, a superposition of all their potential states at once. For Bohr, this uncertainty was not a flaw in the theory. It was a fundamental feature of nature. These quantum things had no independent reality in the ordinary physical sense before we interacted with them. Einstein disliked this idea. He was a realist. He believed in a universe that existed independently of us. The moon, he famously remarked, is still there even when no one is looking at it. For Einstein, the probabilities of quantum mechanics were a sign that the theory was incomplete. He believed there must be deeper, hidden variables that determined the outcome of any measurement, even if we couldn't see them. The debate came to a head in 1935 when Einstein, with his colleagues Boris Podolsky and Nathan Rosen, published a paper. It is now known as the EPR paradox. It was a thought experiment designed to show how strange this new reality had become. Here is the idea. Imagine you create a pair of particles with linked properties. For example, a particle with 0 spin decays into two smaller particles. To conserve the total spin, if one particle is found to be spinning up, the other must be found to be spinning down. They are perfectly anti-correlated. In quantum mechanics, these two particles are described by a single mathematical state. They are entangled. Before you measure them, neither has a definite spin. Now, let the particles travel a great distance apart. An observer, Alice, measures her particle and finds its spin is up. Because their fates are linked, she knows, instantly, that the other particle, now light years away and measured by another observer, Bob, must be down. This is what Einstein called spooky action at a distance. How could Alice's measurement on her particle instantly affect Bob's particle across such a vast distance? It seemed to violate the principle of locality, a cornerstone of Einstein's own theory of relativity, which states that no influence can travel faster than light. For Einstein, there were only two possibilities. One, that quantum mechanics was right, and some spooky action instantly connected the particles. This he could not accept. Or two, the particles were never in a fuzzy state. They had definite, predetermined properties from the start. Like putting one left glove and one right glove into two separate boxes and shipping them across the world. When Alice opens her box and finds a left-handed glove, she knows instantly that Bob has the right-handed one. There is no spooky action. The information was always there, hidden. Einstein argued the particles must carry similar hidden instructions. Bohr's response was subtle. He argued that you could not think of the two entangled particles as separate things. Until a measurement was made, they formed a single, indivisible quantum system, no matter how far apart they were. Alice's measurement was not an action on a distant particle, it was a measurement asterisk on the entire system. The question of how a signal traveled from one to the other was meaningless because, in a quantum sense, they were never truly separate. For decades, this remained a philosophical stalemate. It seemed like a question that could never be answered by experiment. Then, in 1964, a physicist from Northern Ireland named John Stuart Bell came along. On his own time, he wondered about the old debate. He asked a simple question: could you test it? Could you devise an experiment to see whether Einstein's hidden instructions or Bohr's spooky connections were the correct description of reality? The answer, he found, was yes. Before we see how Bell settled this debate, we need a clearer picture of the quantum principles at play. The key is to remember that the quantum world does not follow our rules. Our intuition, shaped by a lifetime with large objects, can be a poor guide. The first concept is asterisk superposition. Quantum mechanics tells us that before measurement, a particle exists in a combination of all its possible states at once. Imagine a coin spinning, not on a table, but in a place almost without time. It is not heads or tails. It is the possibility of both. Only when we measure it, by catching it, does it collapse into a single, definite outcome. This applies to a real quantum property called asterisk spin. For particles like electrons, spin is an intrinsic property like mass. We can imagine it as being either up or down. According to superposition, before we measure an electron's spin, it is in a state of both up and down. When we perform a measurement, it is forced to choose, and it randomly snaps into one of those two states. That is a single particle. Entanglement is what happens when two or more particles are linked so their fates become intertwined. They are no longer independent, they are part of a single quantum state. A common way to create this link is to send a high-energy photon into a special crystal. Occasionally, this parent photon is absorbed, and two new, daughter, photons are emitted. Because of conservation laws, the properties of these two new photons are correlated. Let's use our spin analogy. Imagine a particle with zero total spin decays into two new particles, A and B. Their total spin must remain zero. This means if particle A is measured as spin up, particle B must be found to be spin down. Here is the crucial part. Before measurement, neither A nor B has a definite spin. They exist in a linked state of superposition described by a single equation. The state of this system is A is up and B is down, or A is down and B is up. This is the heart of entanglement. It is not that the particles have opposite properties. It's that neither particle has a definite property until one of them is measured. They exist in an indeterminate state of perfect anti-correlation. In the glove analogy, the properties are predetermined. This is local realism. But for entangled particles, it is more like having two magic coins. When you flip them, they are guaranteed to land on opposite faces. But the strange part is, they do not have faces until they land. The moment coin A lands and shows heads, coin B, no matter how far away, instantly becomes tails and lands that way. The outcome is not predetermined. The correlation is. The two particles behave as a single system. The space between them seems to be irrelevant. This suggested reality was non-local, that what happens in one place could have an instantaneous effect somewhere else. Bell realized that the glove analogy and the magic coin analogy did not just offer different stories. They made measurably different statistical predictions. For nearly 30 years, the battle between Einstein and Bohr was a war of words. A debate for philosophers. Then, in 1964, John Stuart Bell published a short, dense paper. In it, he laid out what is now known as Bell's theorem. Bell wanted to take Einstein's side of the argument seriously and follow it to its logical conclusion. What if each particle really does carry a set of hidden instructions that determines the outcome of any measurement? He created a thought experiment. It uses our observers, Alice and Bob, who receive pairs of entangled particles. Instead of just measuring spin as up or down along one direction, they can each choose to measure along one of three different directions. A, B, or C. They choose their setting for each particle independently and randomly, after the particles are already in flight. First, let's assume Einstein is right, local realism. Each particle leaves the source with a complete instruction set that says what result it will give if measured along A, B, or C, and Alice's measurement cannot affect Bob's outcome because they are too far apart. Alice and Bob run the experiment many times, randomly picking a setting, and later compare their notes. They are interested in the correlation between their results when they happen to choose different settings. Bell's genius was to show, with simple probability theory, that if the particles are following pre-written, local instruction sets, there is a fundamental limit on how correlated their results can be. This mathematical constraint is known as Bell's inequality. Think of it like a survey of pairs of identical twins about 3 yes/no traits. Each twin has a definite answer for all 3 traits. 2 pollsters, Alice and Bob, each randomly ask one of the 3 questions to their twin. Bell's theorem is like saying that if you compare the agreements for different pairings of questions, there's a mathematical limit to how correlated their answers can be. You can only shuffle a finite set of properties around in so many ways. This set up a clear, testable prediction for Einstein's worldview. If local realism is correct, the measured correlations must obey Bell's inequality. Then, Bell calculated what quantum mechanics would predict for the same experiment. He found something astounding. Quantum mechanics predicted that the correlations would be stronger than the limit allowed by local realism. In other words, quantum mechanics violates Bell's inequality. The philosophical debate was over. Bell had transformed it into a physical contest. All that was left was to perform the experiment. The question was no longer, which theory is more pleasing? The question was now, what does the universe actually do? Bell had drawn a line in the sand. On one side was local realism, Einstein's intuitive world. On the other was quantum mechanics, Bohr's strange, interconnected world. It took a few years for technology to catch up, but landmark early tests soon began. One of the first pivotal tests was performed in 1972 by John Clauser and the late Stuart Friedman at the University of California, Berkeley. At the time, pursuing such an experiment was seen as a career risk. But Clauser was determined. Their setup was tabletop-sized, but the question it asked was immense. They used a calcium atom that emitted a pair of entangled photons in opposite directions toward detectors. They ran the experiment, collecting data for hundreds of hours. When they analyzed their data, the result was unambiguous. Their experiment showed a clear violation of Bell's inequality. The data perfectly matched the predictions of quantum mechanics. For the first time, an experiment had shown that spooky action at a distance was a hard, physical fact. But science works by slow correction. Lingering questions remained. Critics pointed out potential loopholes, subtle issues in the design that might allow a local realist explanation to remain. This is where Alain Aspect enters the story. In the early 1980s in Paris, Aspect and his team conducted more refined experiments. To address one loophole, he used ultra-fast switches that could change the measurement setting for each photon while it was in flight. The choice was made so quickly that there was not enough time for any signal, even at light speed, to get from one detector to the other. The result? The violation of Bell's inequality held firm. The spooky correlations remained. For the next 3 decades, physicists worked to design the ultimate Bell test, one that would close all major loopholes at once. This brings us to Anton Zeilinger and the loophole-free tests of 2015. Several teams succeeded. One experiment used 2 entangled electron spins in different labs, separated by 1.3 kilometers. In a later experiment, Zeilinger's group used light from ancient quasars, galaxies billions of light-years away, to determine the measurement settings. The idea was that no conceivable earthly process could have rigged choices made by light that had been traveling since before the Earth was formed. The outcome was, once again, a resounding victory for quantum mechanics. Einstein, for all his genius, was wrong on this point. The universe is not locally real. For this quiet, decades-long search, Clauser, Aspect, and Zeilinger were jointly awarded the 2022 Nobel Prize in Physics. The confirmation was not confined to Earth. In 2016, Chinese scientists launched a satellite named Micius. It created entangled photon pairs and beamed them to two separate ground stations 1,200 kilometers apart. Even across this vast distance, the quantum correlations held. This journey, from a thought experiment to a satellite-based confirmation, represents one of the most profound stories in science. We're about to explore what this means for our idea of reality. So, the experiments have been done. The results are in. What does it mean to live in such a universe? It means we must gently let go of an idea we have always held. That objects are separate and independent things, influenced only by their immediate surroundings. The universe, at its foundation, does not seem to work that way. It is non-local. This brings us back to the idea of distance. For a pair of entangled particles, the space separating them simply does not seem to matter. They behave as a single, unified entity. The concept of distance as a barrier to be crossed appears to be a classical idea, a useful fiction for our large-scale world that breaks down at the quantum level. It is important to be clear about what non-locality does not mean. It does not mean we can send messages faster than the speed of light. Let's go back to Alice and Bob. Alice measures her particle and its state collapses. She knows instantly that Bob's particle is now in the opposite state. But Alice could not control her outcome. The result of her measurement was completely random. Bob, on his end, also sees a perfectly random stream of results. It is only later, when they communicate by normal means and compare their notes, that they see the spooky correlation. The correlation is instantaneous, but information transfer is not. So, if we cannot use it to communicate, what good is it? It is the foundation for a new kind of technology. One application is quantum computing. Classical computers use bits, which are either A0 or A1. Quantum computers use qubits. A qubit can be both a 0 and A1 at the same time. Through entanglement, you can link many qubits together. Their processing power grows exponentially. A quantum computer with just a few hundred entangled qubits could, in theory, perform calculations that would take the most powerful supercomputers billions of years. Another is quantum cryptography. Because any attempt to eavesdrop on an entangled pair disturbs the system in a detectable way, entanglement can be used to create perfectly secure communication channels. If an eavesdropper tries to intercept a particle, the entanglement collapses, and the two parties will immediately know. Finally, there is quantum teleportation. This is not like in Star Trek. It is a way of transferring the state of a particle to a distant one. Using entanglement, you can measure the state of an unknown particle in one location and, by sending classical information, you can perfectly reconstruct that exact quantum state on its entangled partner far away. We began by asking if distance was an illusion. Science has given us a strange and beautiful answer. At the fundamental level of reality, the separation we see is not the whole story. The journey from Einstein's skeptical, spooky action at a distance, to the experiments that proved it real has revealed a universe that is stranger and more deeply interconnected than we ever imagined. The particles that make up your body, the light reaching you from distant stars, everything in our universe was born in the same primordial event. The experiments of Clauser, Aspect, and Zeilinger have shown us that the connections forged in that shared origin can persist across space and time in ways that defy our intuition. We do not yet know the full implications of living in a non-local universe. But one thing is clear: reality is not what it seems. The next time you look up at the night sky, at the quiet dark between the stars, remember that space is not the empty void it appears to be. It is threaded through with invisible, instantaneous connections, a quantum web that binds the universe together. And in that sense, nothing is as far away as it seems. Einstein's spookiest idea proves we are all connected. Imagine a pair of cosmic twins, born from the same event billions of years ago. One particle is here, in a lab. Its twin is on a spaceship, hurtling toward the edge of the galaxy. Here on Earth, a scientist measures our particle and finds its spin is up. Instantly, across that impossible void, faster than any signal could ever travel, its twin assumes the opposite spin, down. There's no communication, no travel time, just a ghostly connection that seems to violate the laws of space and time. This isn't science fiction, it's quantum entanglement, and it's so weird, so contrary to how we think the world works, that Albert Einstein himself refused to believe it. He famously mocked it as spooky action at a distance. He was convinced it was a sign that this new, bizarre theory of quantum mechanics was deeply flawed, and he spent years trying to prove it. But what if Einstein, one of the smartest people who ever lived, was wrong? What if this spooky connection isn't a flaw, but a fundamental truth of our reality? A truth suggesting that the empty space between us is an illusion, that time doesn't flow the way we think it does, and that our powerful, persistent feeling of being a separate I is the most profound illusion of all. Today, we're looking at Einstein's spooky idea. We'll follow the story from a debate between giants of physics to the groundbreaking experiments that finally gave us an answer. We're going to see how one quantum phenomenon unravels our ideas about space, rewrites the nature of time, and reveals a universe that is far more unified and mysterious than we ever imagined. The Great Debate: Einstein versus the Quantum World. To get why Einstein was so bothered by this, we have to go back to the early 20th century. For Einstein, the universe was an orderly, predictable place. It was governed by elegant laws. His theory of relativity painted a picture of a local cosmos. An event happening here could only affect its immediate surroundings, and any influence would spread outwards no faster than the speed of light. A ball is red whether you're looking at it or not. The moon doesn't just disappear when no one is observing it. This idea, known as local realism, was the bedrock of his intuition. The universe, he believed, had definite properties independent of us. As he famously put it, God does not play dice. But a new, rebellious theory was taking shape, one that seemed to love throwing dice. This was quantum mechanics, and one of its key architects, Niels Bohr, had a totally different vision of reality. In the quantum world of atoms and particles, our comfortable, everyday rules just fall apart. One of its wildest concepts was superposition. According to quantum mechanics, before you measure a particle, it doesn't have a definite state. Its spin isn't up or down. Instead, it exists in a fuzzy cloud of all its possible states at once. Think of a spinning coin. It's not heads or tails, it's a blur of both. Only when it lands, when it's measured, does it pick one. This led to an even stranger idea: the observer effect. The very act of measuring a quantum system seems to force it to choose a reality out of that cloud of possibilities. The moment a scientist observes the particle, its fuzzy state collapses into a single, concrete one. This suggested that reality wasn't some pre-written story we were just reading. It was an interactive process, where the observer wasn't just watching, but actively participating in what they saw. This was a nightmare for Einstein. He couldn't accept a universe where things were so uncertain and seemed to depend on us looking at them. He believed the theory wasn't wrong, just incomplete. There had to be, he thought, some hidden variables that determined a particle's state all along. We just couldn't see them yet. The dice, in his view, were loaded. To prove his point and expose what he saw as the absurdity of it all, Einstein, with his colleagues Boris Podolsky and Nathan Rosen, cooked up a brilliant thought experiment in 1935, the EPR paradox. It goes like this. Imagine you create a pair of entangled particles, linked so their total spin must always be zero. If one spins up, the other must spin down. Now, you send these two particles flying off to opposite ends of the galaxy. According to quantum mechanics, neither particle has a definite spin until it's measured. They're both in a superposition of up and down. But the moment you measure the particle on Earth and find its spin is up, the theory says you instantly know the spin of the other particle, light years away, is down. For Einstein, this was the ultimate gotcha. He argued that for this to happen without breaking the cosmic speed limit set by his own theory of relativity, there were only two possibilities. First, measuring one particle sent some kind of instant, spooky, signal to the other. He believed this was impossible. The only other option, he argued, was that the information about their spins was decided from the moment they were created. The particles carried this information with them, like secret instructions. The correlation wasn't spooky, it was predetermined. By not accounting for these hidden variables, quantum mechanics had to be incomplete. He had thrown down the gauntlet. For decades, the EPR paradox was just a philosophical puzzle. Was Einstein right, or was the universe truly connected in this bizarre, non-local way? Physics held its breath, waiting for an experiment that could force the universe to show its hand. The universe's ultimate magic trick, entanglement, unveiled. For nearly 30 years, Einstein's challenge went unanswered. The debate was stuck on blackboards. How could you possibly test a question about the nature of reality itself? Then, in 1964, a physicist from Northern Ireland named John Stuart Bell had a breakthrough. He wasn't content to leave the EPR paradox as a debate. He wanted an answer. So, he came up with a mathematical theorem that could actually be tested. Bell's theorem was basically an ingenious statistical test. It said that if Einstein was right, if hidden variables carried predetermined instructions, then the correlations between measurements on entangled particles could never be stronger than a certain limit. But if quantum mechanics was right, and the particles were part of a single, non-local system, then those correlations would be stronger than Bell's limit. He turned a philosophical argument into a measurable prediction. The universe had to pick a side. It could obey Bell's inequality and prove Einstein's classical intuition right, or it could violate it and confirm the spooky action. Still, testing it was a huge challenge. When a young French physicist named Alain Aspect told Bell he wanted to build an experiment to test the theorem, Bell's first question was, "Have you a permanent position?" He knew it was a risky career move. But the idea was too exciting to ignore. The first to successfully take on the challenge was John Clauser, a researcher at UC Berkeley. Working with Stuart Friedman, he spent 2 years building an apparatus. In 1972, they used calcium atoms that emitted pairs of entangled photons in opposite directions. At each end, a polarizer measured the photon's orientation. After about 200 hours of painstaking data collection, they had their results. The measurements clearly violated Bell's inequality. The correlations were stronger than any hidden variables could explain. The universe did not obey Einstein's local realism. A decade later, Alain Aspect and his team in Paris took the experiment to a whole new level. A potential flaw in Clauser's experiment was that the detectors were fixed. What if they were somehow communicating? To close this locality loophole, Aspect designed a setup that could switch the orientation of the polarizers while the photons were in mid-flight. The switch happened in nanoseconds, so fast that no signal, not even one moving at the speed of light, could travel between them and influence the outcome. The results were the same. Again and again, the universe showed its hand. Bell's inequality was violated. Einstein, for all his genius, was wrong. The spooky action was real. The foundational work of Clauser, Aspect, and later Anton Zeilinger, who performed even more sophisticated tests that closed other loopholes, was so important that they were jointly awarded the 2022 Nobel Prize in Physics. Their experiments proved that quantum entanglement isn't just a quirk. It is a fundamental property of our reality. This discovery is called non-locality. It means that entangled particles aren't two separate things, no matter how far apart they are. They are parts of a single, indivisible system. When you measure one particle, you are gaining information about the entire system, instantly. This doesn't mean we can send faster than light texts. The outcome of any single measurement is still random. It's only by comparing the results from both ends that the spooky correlation appears. But it shatters our classical view of space. Space isn't an empty void that separates things. If the universe is a vast, interconnected fabric, then plucking a single thread here has instantaneous consequences for the whole structure. The confirmation of non-locality was a huge moment in science. It closed a chapter on a great debate, but it opened a door to an even deeper mystery. If particles can be connected across space, what does that say about time? The clock is a lie. How entanglement relates to time. We experience time as a river, flowing relentlessly forward from a fixed past toward an unknown future. It feels like the most fundamental thing there is. And yet, in the world of fundamental physics, that river seems to disappear. One of the biggest challenges in modern physics is the problem of time. Our two main theories of the universe, general relativity and quantum mechanics, treat time in completely incompatible ways. When physicists try to merge them into a theory of quantum gravity, they get a shocking result: equations that describe a static, timeless universe. At the deepest level, the flow of time seems to vanish. So if the universe is fundamentally frozen, where does our powerful feeling of time passing come from? A fascinating idea began to emerge from a very spooky place: quantum entanglement. In 1983, physicists Don Page and William Wouters proposed a radical idea. They suggested that time isn't fundamental at all. Instead, it's an emergent phenomenon, a product of entanglement. Here's an analogy. Imagine the entire universe is one static photograph. Nothing is moving. Now, imagine you define a tiny part of that photo as a clock, and that clock is entangled with the rest of the universe. According to the Page-Wouters mechanism, an observer within that universe, by comparing themselves to the clock, would perceive change and evolution. They would experience a flow of time. In this view, time is a relationship, a correlation between a system and a clock. For a system not entangled with anything, the universe would be completely frozen. Entanglement is what gets the movie projector running, turning the static frames of a timeless reality into the moving picture we experience. For decades, this was just a theory. But recently, experiments have started to back it up, showing in lab settings how the familiar rules of time can emerge from the entanglement between a quantum system and a particle designated as a clock. It seems time isn't something we live in, it's something the universe creates through connection. The quantum world's relationship with time gets even weirder. A team at the University of Toronto, led by Ephraim Steinberg, conducted experiments looking at how long photons spent interacting with a cloud of supercooled atoms. Due to strange quantum interference effects, they measured an average interaction time that was less than 0. Now, this isn't time travel. As Steinberg himself points out, this doesn't mean anything traveled backward in time. But it does show that at the quantum level, our simple, linear ideas about cause and effect get incredibly blurry. So, what does this all mean? Entanglement showed us that space isn't the separator we think it is. And now, it's suggesting that time isn't the absolute river we feel it is. Both appear to be products of a deeper, connected quantum reality. This brings us to the final, and most profound, implication. If the stage on which our lives unfold, space and time, is an illusion born from connection, what does that say about us? The great unveiling, shattering the illusion of self. We tend to see ourselves as isolated individuals, conscious minds locked inside separate bodies, looking out at a world that is other. But what if quantum physics is telling us that this feeling of separateness is the ultimate illusion? Let's go back to the observer effect. The old, and often misunderstood, interpretation was that a conscious mind was needed to collapse a quantum state. A more modern and widely accepted view, known as quantum decoherence, is more subtle but just as profound. It's not about consciousness, it's about interaction. When a quantum system interacts with its environment, a photon, an air molecule, a measuring device, it becomes entangled with it. That interaction forces a choice, and the superposition collapses. The key word is interaction. You can't observe something without becoming physically linked to it at the quantum level. The line between observer and observed blurs away. You are not separate from what you see. This idea has a powerful echo in a school of thought called process philosophy. Thinkers like Alfred North Whitehead argued that reality isn't made of static things at all. It's made of processes, events, and interactions. A rock isn't a solid object. It's a very slow process of vibration and decay. You aren't a noun, you're a verb. You are a continuous process of perceiving, feeling, and interacting. A pattern of energy constantly becoming entangled with the world. And life itself seems to have harnessed this spooky connection. A leading hypothesis for how the tiny European robin navigates thousands of miles with pinpoint accuracy suggests the answer is quantum entanglement. Inside the bird's eye are proteins called cryptochromes. When light hits these proteins, it can create a pair of entangled electrons. The delicate quantum state of these electrons is sensitive to the Earth's magnetic field, allowing the robin to literally see the planet's magnetic lines, giving it a biological compass. While it's not yet definitively proven, the evidence is compelling. The bird's survival may depend on a spooky connection to the planet itself. This forces us to see ourselves differently. The world we experience, of solid objects and separate beings, is a kind of user interface, created by our brain to navigate a much deeper, more connected quantum reality. The idea that your self ends at your skin is a useful illusion for survival, but an illusion nonetheless. Every atom in your body was forged in a star. Every particle has a history stretching back to the Big Bang. Quantum entanglement suggests that the connections forged in that initial, unified state were never truly broken. The particles in your hand and the particles in a distant star are still, in a very real, physical way, part of a single, undivided whole. You are not just a visitor in the universe. You are the universe. You are a localized part of the cosmos that has, for a brief moment, woken up and become aware of itself. The separation we feel is the illusion. The reality is connection. Conclusion. We started with Einstein's discomfort, his refusal to accept a spooky universe. He wanted a world that was local and predictable. But as we've seen, the universe had other plans. A series of Nobel Prize-winning experiments proved him wrong. Spooky action is real. And that one strange fact changes everything. It shows us that the space between us isn't a void, but a bridge. It suggests that time itself emerges from quantum connection. We may even see its signature in the heart of life, guiding a bird across a continent. The ultimate revelation here isn't just about building quantum computers. The deepest truth that entanglement holds up to us is a mirror. It tells us that our most fundamental feeling, that of being a separate, isolated self, is the grandest illusion of them all. We are not islands in an empty sea. We are waves in a single, vast, interconnected ocean. So, the next time you look up at the stars and feel small or alone, remember Einstein's spooky idea. Remember that the same quantum web that links particles across galaxies also links you to that distant star, to the ground beneath your feet, and to the entirety of the cosmos. At the deepest level of reality, we are all connected. If this exploration has sparked something in you, subscribe and join us for more. What other illusions do you think we're living under? Let us know in the comments. Science proves your gaze creates reality. What if the world around us, the solid and definite reality we move through, doesn't fully settle into existence until we look at it? What if our gaze is not just a passive act of receiving information, but a fundamental part of the process that makes the world concrete? This isn't philosophy. It's a question that emerges from the most rigorously tested and deeply strange scientific theory ever conceived, quantum physics. What we have discovered is that at its most fundamental level, reality seems to exist as a shimmering cloud of possibilities, a sea of pure potential. And the act of observation, of measurement, appears to play a crucial role in how this cloud of potential resolves into the single, definite experience we call the real world. This suggests that our perception isn't just a reflection of reality. It might be an inextricable part of it. The grand illusion, your brain as a reality generator. Before we can journey into the bizarre world of quantum mechanics, we must first explore a more intimate, and perhaps equally unsettling, truth. The world you see right now is not the world as it is. It is a story, a simulation, a masterpiece of biological engineering constructed inside your skull. For centuries, we held a simple belief that our eyes were like windows, passively receiving a picture of the world. Neuroscience, however, has shown us that this isn't the case. Your brain, it turns out, is not a simple receiver, it is a prediction engine. Let's begin with a concept from neuroscientist Anil Seth, who describes our waking experience as a controlled hallucination. It sounds radical, but the evidence for it is all around us, and even within us. Consider your own blind spot. In the back of each of your eyes is a point where the optic nerve connects to the retina. At this point, there are no photoreceptor cells. It is a literal hole in your vision. And yet, you don't perceive two black voids in the world. This is because your brain, based on a lifetime of experience, makes an incredibly quick prediction. It guesses what should be there, using the surrounding visual information as a clue, and seamlessly paints it in. You don't see the world and then fill in the gaps. You see the asterisk-filled-in version from the start. Your perception is the edited final cut, not the raw footage. This isn't a minor glitch. It appears to be the fundamental operating principle of our entire perceptual system. According to what is known as the predictive processing framework, the brain doesn't passively wait for sensory signals to arrive before trying to figure them out. That would be too slow, too inefficient for an organism that needed to react instantly to a predator rustling in the bushes. Instead, the brain is constantly running a simulation of the world, generating predictions about what it expects to see, hear, and feel. To illustrate the sheer scale of this internal process, some neuroscientists have proposed that what you perceive is perhaps built mostly on these top-down predictions generated by your brain, with only a small percentage of information coming from bottom-up sensory data from the outside world. That sliver of sensory data acts not as the source of your reality, but as an error correction signal. Imagine your brain as a scientist with a hypothesis. I predict there is a cup of coffee on the desk. It generates the full sensory experience of that cup. Your eyes then send up a stream of data. If the data matches the prediction becomes your reality. But if the data shows the cup is actually slightly to the left, a tiny prediction error signal is sent back up. Your brain doesn't scrap the whole simulation. It just nudges the prediction. The cup is to the left. The hallucination is updated, and the process continues. We see this in our own lives. Have you ever heard a garbled noise, only for it to resolve into clear words once someone tells you what was said? That's your brain receiving a new top-down prediction and using it to retroactively organize the meaningless sensory noise into a coherent perception. This entire system evolved for one primary reason: survival. Our brains are not designed to give us a perfectly objective picture of reality. They are designed to create a useful one. It was far more important for our ancestors to have a brain that could instantly predict the path of a predator from a flicker of movement than to have one that could contemplate the true nature of matter. The reality we experience is a user interface, a set of icons that lets us navigate the world without needing to understand the complex code running underneath. And as we are about to find out, the code underneath is far stranger than we could have ever imagined. The narrator within, how your brain writes your story. If our perception of the world is a constructed simulation, what about our sense of self? That feeling of a single, unified, you, in the driver's seat, experiencing it all? This, too, appears to be a construct, a brilliant and convincing one, but a construct nonetheless. The story of who you are is being written, in real time, by a specific part of your brain. This insight comes from the work of neuroscientist Michael Gazzaniga, who studied patients with split brains. These were individuals whose corpus callosum, the bundle of nerves connecting the brain's left and right hemispheres, had been severed. This created an unprecedented opportunity to study what each hemisphere does when it can no longer communicate with the other. What Gazzaniga discovered was astonishing. The left hemisphere, which is typically dominant for language, seems to contain what he dubbed the interpreter. This is a module with a relentless drive to create explanations, to weave a coherent narrative out of our actions and feelings, even when it has incomplete information. A classic experiment goes like this. An image of a chicken claw is flashed to a patient's right visual field, which is processed by the language-equipped left hemisphere. When asked what they saw, the patient easily replies, "I saw a chicken claw." But then, a different image, a snowy winter scene, is flashed to the left visual field, which is processed by the non-verbal right hemisphere. If you ask the patient what they saw, the speaking left hemisphere, which saw nothing, will report seeing nothing. But here is where it gets strange. The right brain, which did see the snow, can still act. If the patient is asked to point with their left hand, controlled by the right hemisphere, to a related picture, they will correctly point to a shovel. Now comes the crucial moment. The experimenter asks, "Why did you point to the shovel?" Remember, the speaking left hemisphere only saw a chicken claw. It has no idea why the left hand just pointed at a shovel. Does it admit it doesn't know? It never does. Instead, the interpreter instantly fabricates a plausible story. The patient might confidently say, "Oh, that's simple. The chicken claw goes with the chicken, and you need a shovel to clean out the chicken shed." The left brain literally invents a reason that makes sense of the action. This isn't just a quirk of split brain patients. It reveals a quiet, fundamental truth about all of us. We are all constantly driven by subconscious urges, emotional reactions, and biological processes we are not aware of. And our interpreter module works to create a story that makes us feel like rational beings in control. It's a rationalization that happens after the fact. First comes the action or the feeling, and then comes the story about why we did it. The sense of a unified I is, in large part, a narration created after the events it explains. So, we have two profound ideas from neuroscience. First, our perception of the external world is a controlled hallucination. Second, our perception of our internal self is a narrative constructed after the fact. We are living inside a story, generated by and about us. This leads to a quiet, but enormous, question. If the asterisk experience of reality is a construction, what is the raw material? What is the world made of before our brain gets to work on it? To answer that, we have to leave the familiar world of neuroscience and take a journey into the deepest, most mysterious layer of reality known to science, the quantum realm. The quantum abyss, a universe of pure possibility. For more than a century, physicists have been grappling with a truth that quietly dismantles our everyday intuition. The world of solid, predictable objects is an illusion. When you zoom in, past the molecules and atoms, the rules of reality as we know them break down. This is the world of quantum mechanics, And it is here we find evidence that reality isn't a fixed, concrete thing, but a fluid, probabilistic sea of potential that is fundamentally tied to the act of measurement. The cornerstone experiment that throws this into the starkest relief is the famous double-slit experiment. It has been called the central mystery of quantum mechanics, and for good reason. To understand it is to understand that the world is not what it seems. Imagine firing tiny particles, like marbles, at a screen with two thin slits in it. On a detector wall behind the screen, you would expect to see two distinct bands, corresponding to the marbles that pass through each slit. This is logical, and it is exactly what happens. Now, imagine sending water waves toward the same two slits. The waves pass through both slits at once, creating two new wave fronts that interfere with each other. Where crests meet crests, they reinforce. Where crests meet troughs, they cancel out. The result on the detector wall is not two bands, but a series of many bands, an interference pattern. This pattern is the definitive signature of a wave. Here comes the quantum weirdness. Let's now perform the experiment with electrons, fired one at a time. An electron is a particle, a tiny bit of matter, so we would expect it to behave like a marble, creating two bands. But that is not what happens. When we fire the electrons one by one and wait for the pattern to build up, what emerges is an interference pattern. This result is profoundly strange. It means each individual electron, traveling alone, somehow passed through both slits at the same time, like a wave, and interfered with itself. Before it was detected, the electron wasn't a solid point. It existed in a state of superposition, a haze of probability, a wave of potential that encompassed all possible paths. It only became a definite particle at a single location when it hit the detector wall. Now for the part that challenges our view of observation. The physicists, baffled, decided to find out which slit each electron was really going through. They placed a detector by the slits, a device that would do nothing but register which path each electron took. It was a simple act of measurement. The moment they did this, the moment they measured which path the electrons took, the interference pattern vanished completely. The pattern on the wall instantly became the two simple bands we saw with the marbles. The act of measuring which path the electron took was inseparable from the outcome. When its path was unknown, it behaved like a wave of possibilities. When its path was measured, it behaved like a particle on a single, definite path. This is often called the observer effect, or more accurately, wave function collapse. It suggests that at the most fundamental level, the universe exists as a field of pure potential, the wave function, and it is the act of measurement or interaction that seems to force this potential to assume a single, actual value. As the physicist Werner Heisenberg noted, what we observe is not nature itself, but nature exposed to our method of questioning. It is crucial to be clear here. For many decades, physicists have debated what measurement means. The mainstream view is that it does not require a conscious human mind. Any physical interaction that reveals which path information, a photon bouncing off the electron, a detector registering its presence, is enough to cause what's called decoherence, which for all practical purposes collapses the wave function. But this only deepens the mystery. What if the detector itself is a quantum system, and the computer it's hooked up to, and the physicist looking at the screen? This is the essence of the Wigner's friend thought experiment. It suggests a chain of observation that raises quiet, philosophical questions about where the line between potential and actual is truly drawn. At its very foundation, reality is not solid and predetermined. It is a field of potentiality. And the act of interaction and measurement plays a fundamental role in transforming that potential into the actual. The bridge, a speculative frontier. We now stand with two towering ideas. From neuroscience, we have the predictive brain, which constructs our subjective reality. From quantum physics, we have the observer effect, where a field of potential collapses into a single state upon measurement. For decades, these two frontiers developed in parallel. But now, at the very edge of science and philosophy, some are beginning to ask a tantalizing question. What if these two processes, one describing subjective experience, the other objective matter, are somehow related? This is a speculative and profound frontier. One of the interpretations of quantum mechanics that speaks to this is called cubism, or quantum Bayesianism. Cubism proposes a radical shift. It suggests that the quantum wave function, the cloud of possibilities, does not describe the objective state of the world, out there. Instead, it describes the subjective beliefs or knowledge that an asterisk agent has about the potential outcomes of their interactions with the world. In this view, a collapse of the wave function is not a physical process happening in the world. It is the moment an observer updates their beliefs based on the outcome of a measurement. It is a collapse of ignorance, a sharpening of knowledge. The result of the measurement is the agent's new personal experience. This idea resonates in a fascinating way with the neuroscience of the predictive brain. The brain is, in essence, a Bayesian inference engine, constantly updating its beliefs about the causes of its sensory signals to create its best guess of reality. Could it be that the brain's best guess is a neurological echo of this quantum process? That the moment your brain settles on a stable perception, that is a coffee cup, is the subjective experience of information becoming definite? This is not a mainstream scientific theory, and it's important to state that there is no empirical evidence for a direct link. Most physicists point out that the warm, wet environment of the brain would make it impossible to sustain the delicate quantum states required. This remains a question that sits at the intersection of physics and mind, a fringe but fascinating hypothesis. It suggests that consciousness is not a passive spectator, but an active participant in a constant dialogue with the world. The conscious creator, living in a participatory universe. What does all of this mean for us in our daily lives? If taken seriously, the implications are quietly revolutionary. It means the universe is not just something happening to you. It is something happening through you, shaped by the lens of your own perception. Now, to be absolutely clear and honor the science, there is no established theory that proves your conscious thoughts can physically reach out and collapse wave functions in the world. The connection we have been exploring is more subtle and practical. The true power lies in the parallel between how reality operates at its most fundamental level and how your own brain operates. Both are processes of resolving potential into actuality. Consider this. Your thoughts, your beliefs, your focus, and your expectations are the very tools your predictive brain uses to construct your reality. They are the top-down predictions that filter and organize the raw data of life. When you look at your life through a lens of fear, you are, in a very real neurological sense, instructing your brain to become a highly efficient machine for finding evidence that confirms that fear. Your attention becomes a spotlight that illuminates threat and scarcity while leaving opportunities in the shadows. Conversely, when you deliberately cultivate a state of gratitude or possibility, you are changing the core predictions your brain is making. You are training your attention, your active observation, to seek out and notice a different set of possibilities. You begin to perceive solutions where you once only saw problems. The world has not objectively changed, but your subjective experience of it is transformed. This is not magic, it is the science of perception. You are using the very mechanism of your controlled hallucination to consciously choose which hallucination to control. You are becoming a deliberate observer. The feeling of being stuck in life can be reframed as being caught in a repetitive predictive loop. We collapse the same reality, day after day, because we are observing life through the same unchallenged beliefs and unexamined emotions. The key to breaking free is to change the observer, to become aware of the lens through which you are looking, and to consciously choose a new one. Conclusion: We have journeyed from the inner cosmos of the brain to the outer frontiers of quantum physics, and we have arrived at a single, powerful realization. The solid world you see is a story, written by your predictive brain. The self you believe you are is the narrator of that story. And the raw material for that story is a universe of pure potential that takes form through the act of observation and measurement. You are not just a resident of the universe, you are a participant in its unfolding. Your gaze is not just a passive glance, it is part of the process that sculpts the infinite field of what could be into the definite experience of what is. In this great drama of existence, you are both the actor and the audience. So, the only question that remains is the one you must answer every moment of every day. What reality will you choose to observe next? The universe's magic trick: how chaos becomes calm. The world we experience feels solid, stable. The chair you're sitting in, the ground beneath your feet, the quiet presence of the room around you. It all exists with a comforting persistence. You can look away and look back, and trust that it will remain unchanged. But this familiar reality is, in a way, the final chapter of a much deeper story. What we perceive is the result of a quiet, constant process. Backstage, at the most fundamental level of the universe, reality is not so settled. It is a place of pure potential, a subtle stir of possibilities, of maybes and what-ifs. At every moment, an invisible architecture is at work. It is a process so seamless, so fundamental, that we are not even aware of its happening. This process takes the microscopic, uncertain world and, without any sense of performance, allows it to become the calm, classical world we can trust. This is not a story of metaphysics. It is the story of a physical principle, one of the universe's most subtle methods for constructing reality. This is the story of decoherence. And by the end of our journey today, you will understand this process. You will see how the universe uses its own underlying complexity to create order, and why the solid world we know is the quiet, magnificent outcome of a quantum potential. The backstage chaos. Welcome to the quantum world. To understand this process, we first have to go backstage. And the backstage of our reality is the quantum realm. It is a place where the familiar rules of our world give way to something less intuitive. The best way to enter this world is through a doorway that has informed physics for over a century: the double-slit experiment. The setup is simple in its design. Imagine a barrier with two thin, parallel slits. On one side, a source releases tiny particles, like electrons, one after another. On the other side, a detector screen records where each electron arrives. Now, if electrons were like small, solid objects, as our everyday intuition suggests, the result would be straightforward. Some would pass through the left slit, some through the right. On the screen, we would find two distinct bands where they landed, like shadows of the two slits. Simple, predictable, but that is not what is observed. When we release the electrons one at a time, and do not watch which slit they travel through, something else happens. The screen does not show two bands. It shows a pattern of many bands, spread across the screen. This is called an interference pattern, and it is the signature of waves. When waves from two sources overlap, they interfere. Where their crests meet, they reinforce one another. Where a crest meets a trough, they cancel out. The pattern on the screen is a clear sign of wave-like behavior. And yet, we were releasing individual electrons. This result suggests that each single electron, traveling by itself, behaved as if it passed through both slits at the same time, like a wave, and then interfered with itself. This is the first piece of our puzzle, the foundational concept of the quantum world: superposition. A quantum particle, when unobserved, does not have one definite location. It exists in a state of potential, a field of probabilities. It is not simply here or there. It is in a state that includes both here and there, and all other possibilities, at once. An electron is described by a wave function, a mathematical description of this haze of potential. The value of this function at any point tells you the probability of finding the particle there, if you were to measure it. Think of a coin spinning in the air, just before it lands. For a moment, it is neither heads nor tails. It is a dynamic blur of both possibilities. Only when it comes to rest, only when it is measured, does it settle into a single, definite state. An unobserved electron is like this, but for all of its properties, its position, its momentum, and even its spin. It can be in a superposition of spinning, up, and down, simultaneously. So what holds this state of potential together? What allows an electron to maintain its wave-like character? The essential ingredient is asterisk coherence. Coherence is the internal consistency of the wave function. It is the ordered relationship that allows all the possibilities to exist together in a synchronized way. Imagine two swimmers in a pool, moving their legs in a perfectly coordinated rhythm. The waves they create would add up in a clean, predictable interference pattern across the water. That is coherence. It is the pristine, undisturbed state of an isolated quantum system. It is the quiet backstage, where everything is still pure potential. But this brings us to a question that has been at the center of physics for a century: the measurement problem. The moment we try to see which path the electron takes, for instance, by placing a detector at the slits, the wave-like behavior vanishes. The interference pattern disappears. On the screen, we see only two simple bands, just as the classical intuition predicted. The act of observation seems to resolve the uncertainty, forcing the particle to behave like a simple, classical object. For decades, this was a source of deep confusion. Does the universe change its behavior when it is watched? Is consciousness required to bring reality into focus? It felt less like physics and more like something else entirely. This is the great question at the heart of reality. Why does the quantum world of, and, give way to the classical world of, or, simply because a measurement was made? The answer, it turns out, has little to do with us. It has everything to do with the surrounding world. The nosy neighbors, the environment steps in. The picture of the quantum world we've described so far, a single electron, perfectly isolated in a vacuum, is a useful simplification. It is what we imagine in thought experiments. But in the real universe, nothing is ever truly alone. Every system exists within a vast, complex ocean of other things. We call this ocean the environment. And it is perhaps the most important character in our story. What is the environment? It is everything else. It is the countless air molecules in the room. It is the photons from a light source, or the faint, ever-present thermal radiation that fills all of space. It is the small vibrations within the material of the experiment itself. The universe is not a sterile laboratory, it is a busy, interconnected place. Every quantum system has billions upon billions of neighbors, and they are constantly interacting. This is where the next crucial piece of our puzzle comes into play: entanglement. When our quantum system, our electron, interacts with just one of these neighbors, say, a single photon of light scatters off it, the two become linked. Their states are now intertwined. They are entangled. Entanglement means you can no longer describe the electron without also describing the photon. They have become part of a single, larger quantum system, described by one shared wave function. Imagine our electron is in a superposition of being in position A and position B. If a photon interacts with it, that photon's resulting path is now correlated with the electron's position. A photon scattering from position A will travel in a different direction than a photon scattering from position B. The state of the combined system is now something like: electron at A and photon went left, plus electron at B and photon went right. The quiet consistency has been disturbed. The information about the electron's superposition, its coherence, the precise relationship between its different possibilities, is no longer contained only within the electron. It has been shared. It has become distributed into the environment. The photon now carries a record, a piece of information about the electron's state. This is the heart of the mechanism. Think of coherence as a quiet, private thought. As long as it remains unshared, it is pure and complete. But what happens if that thought is spoken aloud, and a friend hears it? And that friend mentions it to others? The information spreads. As it spreads, it becomes part of the vast, complex network of conversations in the room. To reconstruct the original, pristine thought, you would now have to find every single person who heard a piece of it and assemble their fragmented, noisy versions. It becomes a practically impossible task. Our electron's coherence is like that quiet thought. The environment is the crowd. Every time a particle from the environment interacts with our electron, it is like another person learning a piece of the information. A single air molecule bumping into it, a single thermal vibration. Each interaction creates another entanglement, spreading the quantum information further and further away. The coherence that was once held neatly within the electron is now distributed, impossibly thin, across a gigantic, complex system made of the electron and every particle it has touched. This process, where a quantum system becomes progressively entangled with its environment and its internal coherence is shared with the outside world, has a name. It is the process itself. It is decoherence. This process, this distribution of information, is the key to understanding how our stable reality is formed. Just as a single concept like decoherence can provide a foundation for understanding the classical world, building your own knowledge requires a solid base. And there's no better place to build that base than with Brilliant. Brilliant is an interactive learning platform that helps you understand concepts in math, science, and computer science through hands-on problem solving. Instead of just passively watching, Brilliant allows you to become an active participant. You learn by doing. If you are interested in the quantum concepts we are discussing today, Brilliant has entire courses that will walk you through the logic of quantum mechanics, from superposition to entanglement. You can build your intuition one puzzle at a time, making complex ideas feel clear and accessible. Their courses are laid out like a story, guiding you from basic principles to advanced topics in a way that feels like a journey of discovery. To support our channel and start your own journey, you can go to brilliant.org/universesmagictrick or click the link in the description below. The first 200 people to sign up will get 20% off an annual premium subscription. Now, back to our quantum information, which has just been shared with the vast, complex crowd of the environment. What happens when that sharing becomes constant and overwhelming? The magic trick revealed. Decoherence takes the stage. We've arrived at the central idea. Decoherence is the process by which a quantum system loses its apparent quantumness through interaction and entanglement with its environment. It is the mechanism that bridges the gap between the world of potential and the world of the actual. Let's return to the double-slit experiment. We now understand that the interference pattern depends on the electron's coherence, the synchronized consistency of its wave function. But in any real experiment, the electron is not in a perfect vacuum. As it travels, it is inevitably nudged by stray photons, air molecules, and other environmental noise. Each of these small interactions entangles the electron with a piece of its environment. Each interaction, in a way, measures the electron's position, and that information is carried away. The phase relationship that allowed the through the left slit possibility to interfere with the through the right slit possibility is no longer a property of the electron alone. It's now a shared property of the electron and a vast, untraceable number of environmental particles. To see the interference pattern, one would need to know the complete state of every single particle that the electron interacted with. You would have to gather all the distributed pieces of information and put them back together perfectly. This is not just practically difficult, it is, for all intents and purposes, impossible. The information is lost to observation, dissipated as heat and microscopic disorder into the universe. This is what obscures the interference. Remember our synchronized swimmers creating clean waves? Now, imagine hundreds of people randomly splashing in the pool. The delicate, ordered waves of the swimmers are gently washed out by the random noise. You can no longer see their clear interference pattern. The information is still there, the swimmers are still swimming, but it is buried, completely obscured by the chaotic splashing of the crowd. Decoherence is the universe's way of constantly creating these small disturbances. This gives us a more physical, and less mystical, explanation than the old idea of wave function collapse. The wave function doesn't mysteriously pop out of existence when a conscious observer looks. Instead, decoherence explains that the environment itself acts as a relentless, ubiquitous observer, constantly measuring the system. The quantum strangeness does not vanish. It just becomes so thoroughly entangled and distributed across the environment that it is no longer locally observable. What is left, from our perspective, looks like a classical outcome. The system has decohered into a statistical mixture of states. It behaves as if it's 50% here and 50% there, but the interference, is gone. But decoherence does more than just obscure quantum interference. It also helps to select the states that are stable enough to exist in our classical world. This is the idea of environment-induced superselection, or asterisk pointer states. Think of a pencil balanced perfectly on its sharp tip. This is like a quantum superposition, a fragile, unstable state. The slightest vibration, the gentlest breeze, the smallest interaction with the environment, will cause it to fall. And it will always fall into a stable state, lying flat on the table. Once it is flat, further breezes have very little effect on it. The lying flat state is robust. It is a stable, pointer state that is resistant to further environmental disturbance. In the same way, quantum superpositions are like the pencil balanced on its tip, incredibly fragile. Classical states, like a particle having a definite position, are like the pencil lying flat, incredibly robust. The environment is the constant breeze that relentlessly causes fragile quantum states to settle into the stable, classical pointer states. The universe, through decoherence, naturally favors states that are stable and do not change when gently prodded. This is why we perceive objects as having definite locations. A cat in a superposition of here and there would be instantly decohered by interacting with air molecules and photons into a state of here or there. And this process is exceptionally fast. For a macroscopic object, it is virtually instantaneous. A tiny speck of dust is bombarded by an enormous number of air molecules every second. Each collision is an act of decoherence. A superposition of the dust speck being in two places at once would resolve in a time so short it makes a nanosecond seem like an eternity. Physicists have calculated these timescales, and they are often fractions of a picosecond. This is why we never see Schrödinger's cat in a superposition of alive and dead. A cat is a macroscopic object, interacting with its environment in countless ways every instant. Its state is being measured by the environment so thoroughly and so rapidly that any quantum superposition is destroyed almost before it can form. The process is complete. The potential has resolved into the actual. The grand performance, from chaos to calm reality. Now we can zoom out and see the full picture. We can begin to understand why the world you experience is so reassuringly classical and solid. Consider the chair you are sitting in. It is made of a truly vast number of atoms. Each of those atoms, by itself, is a tiny quantum system, governed by the laws of superposition and probability. So why doesn't your chair behave like a quantum object? Why doesn't it exist in a superposition of being in your room and on the moon? Because of decoherence, scaled up to an almost unimaginable degree. Every single one of those countless atoms is constantly interacting with its neighbors. They vibrate, they bump into each other, and the entire chair is being bombarded by photons and air molecules. The sheer number of these interactions is astronomical. Any trace of quantum coherence that might exist in one atom is instantly shared, entangled, and washed out across the entire collection. The uncertainty of all those individual quantum possibilities effectively averages itself out. It is the law of large numbers applied to reality itself. The quantum potential of one atom is balanced by the potential of its trillions of neighbors. What emerges from this microscopic, complex activity is an incredibly stable, robust, classical average. The chair remains where it is because the overwhelming, relentless process of decoherence has resolved its properties into a definite state. The calm we perceive is born directly from the underlying complexity. This perspective might even shed some light on one of the deepest questions in physics: the asterisk arrow of time. Why does time appear to flow in only one direction? Why can we remember the past but not the future? Decoherence is an irreversible process. Once that quantum information, that coherence, has been distributed into the environment, you cannot easily get it back. It is like trying to unscramble an egg or unmix cream from coffee. The information has dissipated as entropy, as microscopic disorder, and the path back is effectively closed. This one-way flow of information, from a pure, coherent state to a messy, decohered state, looks very much like the thermodynamic arrow of time. The past could be seen as the definite, decohered state of the universe of which we have a record, while the future remains a realm of coherent, quantum possibilities waiting to be resolved. The now is the constantly advancing wavefront of decoherence. So, does this finally solve the measurement problem? It is important to be intellectually honest here, because this remains a frontier of physics. Decoherence brilliantly explains how a quantum system loses its quantum properties and comes to look classical. It explains why we do not see macroscopic superpositions. It solves the practical problem of the quantum to classical transition. It demystifies the process, removing the need for a conscious observer and replacing it with the physical, measurable effect of the environment. However, it does not entirely eliminate the foundational philosophical question. The debate simply shifts. The old question was, what causes the wave function to collapse to a single outcome? The new question becomes, decoherence leaves us with a menu of classical possibilities, a statistical mixture. Why do we, in our experience, perceive only one of those outcomes? For proponents of the many worlds interpretation, decoherence is a key mechanism. They argue that decoherence does not eliminate possibilities, it simply separates them into non-interacting, parallel branches of reality. In one branch, the electron went left. In another, it went right. The cat is alive in one universe and dead in another. Decoherence is what causes these branches to split and go their separate ways. For other physicists, decoherence is the process that prepares the system for a final, still unexplained, collapse event. But what decoherence has done is move that seemingly strange moment out of the realm of everyday interactions and into the deep, unresolved foundations of the theory itself. Conclusion. So, let us revisit the process we set out to understand. We started with a profound observation: a universe that appears to operate on two different sets of principles. A probabilistic and potential quantum world backstage, and a solid, predictable, and calm classical world on the main stage. We followed the evidence. We saw how superposition allows for a realm of possibilities, and how coherence maintains the internal consistency of that realm. Then we introduced the rest of the system, the endless sea of environmental particles. We discovered that through entanglement the quantum information of coherence inevitably gets shared, distributed into the environment until it is irretrievably dispersed. And that was the resolution. Decoherence. It is not a sudden event. It's a relentless, physical process, a kind of fundamental condition that is happening everywhere, all the time. The agent of this process is not a conscious mind, but the universe itself, through the constant, quiet hum of interaction. The stable reality you experience is not a fragile illusion. It is an incredibly robust, emergent property. The world feels solid and dependable not in spite of the underlying quantum nature of things, but because of it. The universe's quiet work is to use its own inescapable complexity to produce order. The calm you perceive is the magnificent, silent settling of countless quantum possibilities into a single, real, and observable world. Your brain might be a quantum computer. You are having a thought right now. Perhaps a simple one, the decision to continue listening. For a long time, science has told a story about how such a choice happens. It's a story of electrical signals moving between neurons, a delicate cascade of chemistry across synapses, all unfolding within the quiet, 3-pound universe of the brain. The brain, in this story, is a biological computer, processing information to arrive at an answer. It is a good story, a powerful one. But it may not be the whole story. What if that decision was not only the result of electrical patterns in a biological machine? What if, in this moment, your awareness reached into the fundamental structure of the universe, touched the strange and subtle rules of quantum mechanics, and collapsed reality into the single outcome that is your experience? A Nobel Prize-winning physicist came to believe this was not only possible, but likely. If he is right, it could change our understanding of who, and what, we are. This is not science fiction. It is a scientific idea that, after decades of criticism, is finding quiet, new support. Before we explore that deeper landscape, let's begin on solid ground, with the brain as classical neuroscience has come to know it. For more than a century, the most successful model of the brain has been that of a biological computer. An incredibly complex one, with around 86 billion neurons, each one a kind of organic switch. These neurons are connected by a vast network of 100 trillion synapses, a web so intricate it makes our global internet seem like a simple sketch. In this model, every thought and memory is held in patterns of electricity. A neuron rests, holding a small electrical charge. When stimulated by its neighbors, it reaches a threshold and sends an electrical spike down its length. When this signal reaches a synapse, it releases chemical messengers, neurotransmitters, that cross a tiny gap to the next neuron, encouraging it to fire or suggesting it remain quiet. It is a beautiful, intricate dance of electricity and chemistry, a system of inputs, processing, and outputs. And this model has been powerful. We can watch the brain at work with fMRI scans, seeing regions light up as a person recognizes a face or feels an emotion. We understand how certain medicines can alter our mood by shifting the chemical balance in our synapses. This classical view of the brain is a cornerstone of modern medicine and psychology. It has explained a great deal about how we function, how we learn, and what happens when the system is disturbed. Neuroscientists sometimes refer to the questions this model can answer as the easy problems. They are not easy in the sense of being simple, their complexity is monumental. But they are, in principle, solvable. They are problems of mapping the structure and tracking the signals. How does the brain turn sound waves into the experience of a symphony? We can trace the pathway from the ear to the auditory cortex. How do we learn a new skill? We can observe how synaptic connections strengthen or weaken over time, a process known as neural plasticity. This is the brain as a magnificent, self-organizing biological machine. It takes in data from the world, processes it through its intricate network, and produces a response. You see a threat, your visual cortex processes the information. Signals travel to the amygdala, adrenaline enters your system, and you react. It is cause and effect. It is deterministic. And for a long time, it felt as though if we could just map all the connections, we would have solved the mystery of the mind. But there is a quiet, profound question at the center of this beautiful mechanical explanation. The classical model of the brain is brilliant at explaining how the brain works. It can, in theory, map every neural firing that happens when you taste a strawberry. It can trace signals from your taste buds to the gustatory cortex and identify the regions associated with pleasure and memory that become active. It can describe the entire process. But it does not explain one fundamental thing. Why does it feel like something to taste that strawberry? Why is there an experience of redness when you look at an apple? The brain is processing photons of a specific wavelength, around 650 nanometers. We can describe that process perfectly. But why does that information processing appear in your mind as the subjective, qualitative feeling of red? Why is it not all just information being processed in the dark, without an inner world, without any awareness at all? This is what the philosopher David Chalmers named the hard problem of consciousness. It is the question of why and how physical processes in the brain give rise to subjective experience, what philosophers call qualia. The feeling of warmth from the sun, the sting of a difficult memory, the joy of hearing a piece of music you love. These are the textures of our inner life. Think of it this way: one could, in principle, build a perfect android that mimics a human in every way. It could be programmed to say, ouch, when damaged, to write poetry about love, and to laugh at a joke. Its internal processors could be doing everything our neurons do. But a question would remain: would there be anyone home? Would it actually feel pain, or just run a pawn subroutine? Would it experience love, or just execute behaviors associated with the word? The classical, computational model of the brain offers no bridge between the physical processing and the subjective experience. There is nothing in the language of neurons and synapses that explains the emergence of a first-person perspective, the feeling of being you. It describes a complex biological system, but it cannot explain the awareness that experiences it. This is not a small gap in our knowledge, it is the central mystery of neuroscience. And it has led some of the most brilliant minds in science to wonder if we have been looking in the right place. They argue that if a system based entirely on classical physics cannot account for the most obvious fact of our existence, our own awareness, then perhaps the answer lies in a deeper, stranger set of physical laws. So, if the classical model, for all its explanatory power, has this quiet question at its heart: where do we look next? If the answer is not in the signals between neurons, could it be somewhere else? Could it be deeper inside them? This question is what led a few pioneering thinkers to turn to the strangest and most successful theory in all of science: quantum mechanics. Quantum mechanics is the rulebook for the universe at its most fundamental level, the level of atoms and the particles within them. And at that level, reality behaves nothing like the solid, predictable world we experience. Particles do not have a definite location. They exist in a cloud of probabilities, a state of superposition, meaning they can be in many places at once. Particles can become entangled, linked in a way that what happens to one instantaneously affects the other, even if they are light years apart. In the quantum realm, the universe is not a collection of tiny, solid objects. It is a shimmering, probabilistic sea of potential. For most of the 20th century, the consensus was that this quantum strangeness was confined to the subatomic world. In a large, warm, wet system like the human brain, these delicate quantum states would be instantly disturbed by the surrounding noise. The brain, it was agreed, was a classical system. But a few people were not so sure. One of them was Sir Roger Penrose. Penrose is a mathematical physicist whose work on black holes was so groundbreaking it earned him the Nobel Prize in Physics in 2020. He is a core architect of our modern understanding of the universe. And Penrose was deeply troubled by the hard problem of consciousness. He was also convinced, through complex mathematical arguments, that human consciousness did something that no classical computer could ever do. It possessed genuine understanding, a kind of non-algorithmic insight. A computer can follow rules, but it cannot understand them. Around the same time, an anesthesiologist in Arizona named Stuart Hameroff was wrestling with a related mystery from a different field. His job was to turn consciousness off and on every day. He knew that certain anesthetic gases could render a person completely unaware, yet the mechanism was a puzzle. Hameroff began to suspect that anesthetics worked at a much deeper, subcellular level. In the early 1990s, Hameroff read Penrose's book, The Emperor's New Mind, where Penrose laid out his arguments for a quantum basis for consciousness but admitted he had no biological candidate for where this could happen in the brain. For Hameroff, a quiet connection was made. He believed he knew the exact location. He contacted Penrose, and one of the most interesting collaborations in modern science was born. Together, they proposed a theory called orchestrated objective reduction, or OR. It is a direct and radical attempt to explain consciousness. Their proposal was this: consciousness does not come from the electrical activity between neurons. It comes from quantum computations happening inside the very molecular skeleton of our neurons. They proposed that our brains were not just classical computers, they were quantum computers. And that each moment of conscious awareness was, quite literally, a small collapse of reality happening within our skulls. To understand the OR theory, we need to look closer. Way closer. Forget the brain as a whole, or even a single neuron. We need to dive deep inside the cell, past the membrane and the nucleus, into the very structure that gives the cell its shape. We are going to the microtubules. For a long time, microtubules were seen as little more than the cell's scaffolding. They are tiny, hollow cylinders made of a protein called tubulin, forming the cell's internal skeleton. They act as highways for transporting molecules and play a key role in cell division. They were thought to be structurally simple. Hameroff, however, saw them as something more. He saw them as sophisticated information processors. He proposed that these microtubules, with their complex, crystalline structure, were the perfect place to host the quantum effects Penrose was looking for. This is the stage for their idea. According to Penrose and Hameroff, the tubulin proteins within these microtubules are not just simple on or off switches like the bits in a classical computer. They are quantum bits, or qubits. Because of a quantum phenomenon called superposition, a single tubulin protein can exist in a state of being both on asterisk and off at the same time. It is not a 0 or a 1. It is a quiet, probabilistic blend of both possibilities. Now, imagine this scaling up. A single neuron contains millions of microtubules, each made of thousands of these tubulin proteins. In the OR theory, these tubulin qubits can become quantumly entangled, linked together in a vast, coherent quantum state. This coherent state, this symphony of overlapping possibilities spreading through the microtubule network of the brain, is a state of pre-consciousness or unconscious potential. It contains a multitude of possible realities, all existing at once. But we do not experience a multitude of realities. We experience one, definite, conscious moment at a time. This is where Sir Roger Penrose's most unique contribution comes in: the concept of asterisk objective reduction. In standard quantum mechanics, it is often said that the act of observation forces a quantum system to choose one state. Penrose found this unsatisfying. He proposed a different solution, connecting quantum mechanics with Einstein's general relativity. He argued that when a particle is in superposition, in two places at once, it creates two tiny, separate curvatures in the fabric of spacetime. This creates a tiny conflict in the fundamental geometry of reality. According to Penrose, this state is unstable. Spacetime does not like being pulled in two directions at once. After a specific amount of time, the conflict becomes too great, and the system spontaneously and objectively collapses into a single state. The universe itself makes the choice. And here is the heart of the theory. Penrose proposed that this moment of objective reduction is a moment of consciousness. Each self-collapse is a discrete flash of awareness. It is a non-computable event, something that cannot be simulated by a classical algorithm that selects one reality from a sea of potential. This, he argued, is the physical basis for a flash of creative insight, or the simple, subjective feeling of seeing a color. Putting it all together, the theory is called orchestrated objective reduction. The orchestration is Hameroff's part. The quantum superpositions in the microtubules are not random. They are guided and shaped, orchestrated by the classical processes of the brain, like the firing of synapses. These inputs tune the quantum state. The state of quantum possibilities evolves until it reaches Penrose's objective threshold for collapse. At that moment, an objective reduction occurs. A moment of conscious experience happens. A specific set of tubular states is chosen, which then influences the classical firing of the neuron, creating a continuous loop between the quantum and classical levels. Our stream of consciousness, in this view, is a sequence of these quiet, discrete quantum collapses, like the individual frames of a film, happening millions of times a second all over the brain. And this provides a potential explanation for Hameroff's original puzzle: anesthesia. The theory suggests that anesthetic gases have the right properties to get inside the microtubules and dampen these delicate quantum vibrations, preventing them from reaching the collapse threshold. The potential is still there, but the collapse is silenced. Consciousness is turned off. An extraordinary idea requires careful examination. And for decades, the OR theory faced a significant and long-standing problem: decoherence. The argument, most forcefully made by physicist Max Tegmark in 2000, was simple. The brain is a warm, wet, and noisy environment. Quantum states are famously fragile and can only maintain their coherence in extremely cold and isolated conditions. Tegmark calculated that any quantum state inside a microtubule would be destroyed by its environment in femtoseconds, a millionth of a billionth of a second. This is a timescale a billion times shorter than that of neural processes. It was like trying to build a delicate ice sculpture in a blast furnace. For most of the scientific community, this argument seemed to close the door on the idea. The theory was largely dismissed. For 20 years, OR remained on the scientific fringe. But science does not stand still. A growing body of research into quantum biology has shown that nature might be better at protecting quantum effects than we once thought. We now have evidence that photosynthesis relies on long-lasting quantum coherence to efficiently transfer energy. Some birds may use quantum entanglement in their eyes to navigate. The warm, wet world of biology was not as hostile to quantum mechanics as we had assumed. Then, in 2024, a series of findings brought OR back into discussion. One significant paper showed that networks of certain molecules within microtubules could support a collective quantum effect called superradiance at room temperature, on a biologically relevant scale. It was a direct experimental challenge to the earlier decoherence argument, suggesting microtubules might have a built-in way to sustain quantum phenomena. In another study from 2024, a team at Wellesley College revisited Hameroff's original question about anesthesia. They found that rats given a drug that specifically stabilizes microtubules took significantly longer to become unconscious from anesthesia. This suggests that anesthesia does indeed act on microtubules, providing an experimental link between the structure Hameroff identified and the switching off of consciousness. These new findings do not prove OR is correct. But they have reopened a conversation. They have provided concrete, experimental evidence that the core components of the theory, long-lasting quantum effects in microtubules, are not just an abstract idea, but something that can be tested. Penrose himself, in a 2022 interview, acknowledged the theory had been rough around the edges, but stated, People used to say it is completely crazy, but I think people take it seriously now. It is important to draw a line here. OR is a specific, mechanistic theory about quantum computation in the brain. It has sometimes been confused with quantum mysticism, but the theory itself is not a license for magical thinking. The debate is far from over, but for the first time in decades, the proponents of a quantum brain have new experimental data to consider. Let's allow ourselves to wonder for a moment. If Penrose and Hameroff are right, what would it mean? The implications would be quietly revolutionary. First, consider the debate about free will. In a classical, deterministic brain, every action is the predetermined result of a prior chain of cause and effect. But in the OR model, a moment of consciousness, a quantum collapse, is a non-computable event. It is not strictly determined by the state that came before it. This does not grant us limitless free will, but it suggests that our choices are not simply the end of a long chain of events. They are influenced by our history, but emerge from a field of possibilities. Second, it would reframe our approach to artificial intelligence. Penrose has long argued that a classical computer can never achieve true consciousness because it is purely algorithmic. It can simulate, but it cannot understand. If OR is correct, then to build a conscious AI, we would need to build a new kind of machine. A quantum computer that could physically replicate orchestrated objective reduction. Consciousness would not just be a matter of processing power. It would be a specific physical process, tied to the structure of reality. Finally, and most profoundly, it would change our place in the cosmos. In the classical view, consciousness is a fortunate accident, an emergent property of complex matter that arose late in the history of the universe. In the OR view, the fundamental building blocks of consciousness, the moments of objective reduction, are woven into the fabric of spacetime itself. Penrose calls them proto-conscious moments. They are happening all the time, everywhere. The brain, with its uniquely structured microtubules, did not invent consciousness. It evolved to amplify and orchestrate it. This would mean that consciousness is not an afterthought of the universe. It is a fundamental property of it. Our awareness, in this sense, is a direct expression of its deepest physical laws. We began this journey with a simple thought. That path has taken us from the familiar world of neurons, down into the quantum realm inside our cells, and out to the very structure of spacetime. We have seen the elegant and powerful classical model of the brain, and we have sat with the quiet, hard problem that it does not seem to answer. The simple, undeniable fact of our own experience. Into that quiet space stepped the idea of orchestrated objective reduction, which proposes that our brains are quantum computers, and our consciousness is a sequence of collapsing realities. For decades, this idea was a beautiful but seemingly fragile one. But now, recent discoveries have sent a subtle tremor through the debate. Experiments are showing that the brain may indeed be capable of protecting and using the very quantum effects that OR requires. The case, long thought closed, is being re-examined. We do not have a final answer. We are standing at the edge of human knowledge, looking into the deepest mystery there is. The conversation is not over. But the field of possibility has grown wider. So, the next time you have a thought, a flicker of an idea, a memory, or the simple experience of making a choice, ask yourself, is it just electricity flowing through a biological machine? Or is it something more? Is it a quiet symphony, playing on the very fabric of reality? A moment of the universe itself, waking up inside you? What do you think? Is consciousness a classical computation or a quantum phenomenon? Let us know your thoughts in the comments below. And for more calm explorations into the biggest questions in science, consider liking the video and subscribing to the channel. Why 100% certainty is a myth according to science? There is a deep human need for certainty. A feeling that we cannot move forward with a decision until the path ahead is perfectly clear. We spend much of our lives trying to build this certainty. We make 5-year plans. We create routines. We seek reassurance from others. All of it is an effort to secure the future and quiet the feeling of unease that comes with the unknown. We want to feel solid ground under our feet. But the universe, at its most fundamental level, seems to have a rule that makes this kind of certainty impossible. And this is not a mistake. It is a feature of reality. One that, when understood, can offer a quiet kind of freedom. This is not a philosophical idea alone. It is a finding from the deepest layer of the world we have ever explored, the strange and quiet realm of quantum mechanics. Today, we will look at this principle. We will see how it changes our understanding of the world, and how embracing the universe's own uncertainty can change our lives. It can turn the search for solid ground into a calmer dance with what is possible. The human problem, our need for an answer. The search for answers is not a personal flaw. It is a deep part of our biology. Our brains are, in essence, machines that make predictions. From an evolutionary standpoint, this makes sense. For early humans, the ability to predict was a matter of survival. A rustle in the bushes was either the wind or a predator. A strange colored fruit was either nutritious or poison. The brain that could recognize patterns and reduce uncertainty was the brain that was more likely to survive. This mechanism is still active within us. Neuroscientists have found that uncertainty quietly activates the parts of our brain associated with fear and alarm. When we do not know what is coming, our minds register it as a potential threat. The modern world can amplify this feeling. We live in a time that often presents the idea of having life figured out as a goal. We see stories of lives that appear perfectly planned. We are encouraged to have a clear path from a young age. The message is often that certainty is a sign of success, and ambiguity is a sign of failure. This pressure can lead to what psychologists call an intolerance of uncertainty. It is a quiet bias that is a feature of anxiety. We come to believe we must have all the information before we can act. Should I take this job? Should I move to this city? We can become stuck, endlessly weighing options, believing that a perfect, risk-free answer must exist somewhere. The search for certainty does not bring peace. It often creates more anxiety. The feeling of being certain is an emotional state, not just an intellectual one. It provides a sense of reward, which is why simple, solvable puzzles can feel satisfying. They offer a small and safe dose of certainty in a world that rarely provides it. This need for control extends beyond our own lives. We often want our leaders to be decisive and our science to be absolute. We build belief systems, political, religious, or ideological, that give us a sense of order. These systems can feel like a buffer against the complexity of the world. They can tell us what to think and how to act. When we encounter information that challenges these beliefs, our first instinct is often not curiosity, but defense. We filter what does not fit to protect the comfort of our certainty. Philosophers have long observed this impulse. Friedrich Nietzsche wrote about our powerful drive to believe that certainty is the highest value. He asked why we prefer truth to untruth, or to uncertainty, or even to ignorance. His point was that a relentless demand for simple answers can make us blind to the complex and subtle nature of life. We want a simple story, but reality is often a long and complicated novel. So we find ourselves in a contradiction. Our brains are built to seek order. Our culture often tells us this is the goal. Yet, we can sense that life is not predictable. We see our best plans change. We see unexpected events alter the course of our lives. We feel the tension between our desire for a map and our experience of a landscape that is always changing. For a long time, we could imagine this was because of our own ignorance. We simply had not collected enough information. The universe, it was thought, was like a giant clockwork machine. If we knew the position and motion of every part, we could predict its entire future. It was a deterministic idea. A comforting one. But then, in the early 20th century, science looked into the heart of reality. And what it found there was not the certainty we were looking for. It was a universal and unbreakable rule that forbids it completely. It told us that the universe, at its foundation, is built on uncertainty. The universal rule, Heisenberg's revelation and a probabilistic reality. For centuries, the vision of classical physics, from figures like Isaac Newton, was one of perfect predictability. The universe was seen as a grand machine. If you could know the precise position and momentum of every particle at one moment, you could, in theory, calculate its entire past and future. This idea shaped our view of the world. It reinforced the feeling that with enough information, 100% certainty was possible. Then, in 1927, a German physicist named Werner Heisenberg found that this was not the case. He introduced a concept that would quietly redefine our understanding of reality: the uncertainty principle. In its simplest form, the uncertainty principle says there is a fundamental limit to how precisely we can know certain pairs of properties of a particle at the same time. The most well-known pair is position and momentum. Momentum is an object's mass combined with its speed and direction. What Heisenberg discovered is that the more precisely you measure a particle's position, the less precisely you can know its momentum. And the more precisely you measure its momentum, the less precisely you can know its position. It is important to understand what this means. This is not a limitation of our measuring tools. It is not like trying to measure a table with a blurry ruler, a problem we might one day fix with better technology. The principle describes a fundamental feature of the universe. The very idea of an exact position and an exact momentum, existing at the same time, has no meaning in nature. To understand this, we have to change our picture of a particle. We imagine an electron as a tiny, solid ball. But quantum mechanics tells us this picture is wrong. At the subatomic level, everything has what is called wave-particle duality. This means that particles like electrons sometimes act like localized points, and other times they act like spread-out waves. Think of a wave in a pond. Where is its exact position? The question does not really make sense. A wave is a disturbance spread out over a region. It does not have a single location. It has a wavelength, which is related to its momentum. A wave with a very clear, consistent wavelength has a precise momentum. But because it is so spread out, its position is very uncertain. Now, imagine you want to create a wave that is more localized, more like a particle. To do this, you have to add together many different waves with different wavelengths. As you add them, they interfere with each other, canceling out in most places but adding up in one small region. This creates a wave packet. Now you have a much better idea of its position. But because you had to mix together a whole range of different wavelengths, its momentum is now very uncertain. This is the trade-off at the heart of the uncertainty principle. You cannot have both at the same time, because the universe is not built that way. This wave-like nature is the source of one of the most famous experiments in physics, the double-slit experiment. Imagine a barrier with two thin slits. If you shoot small particles, like grains of sand, at it, they will form two lines on a screen behind the barrier. This is simple, particle-like behavior. Now, do the same with waves. When the waves pass through the two slits, they spread out and interfere with each other. The result is not two lines, but a pattern of many alternating stripes. Here is where it becomes strange. If you fire electrons, which we think of as particles, one at a time, you would expect them to make two lines. But they do not. As the individual electrons build up a pattern on the screen, what appears as an interference pattern, just like the waves. This implies something quiet and strange. Each electron, traveling by itself, seems to pass through both slits at the same time. It behaves like a wave of possibility that interferes with itself. Before it is detected, the electron is not in a single place. It exists in a state of superposition, a probabilistic combination of all its possible paths. The electron is not in slit A or slit B, it is in a state of A and B. This is the default state of reality at the quantum level. Not definite things, but a haze of overlapping possibilities. This has been confirmed by many experiments. Radioactive decay is one example. We can predict with great accuracy how long it will take for half of a large number of uranium atoms to decay. But for any single atom, its exact moment of decay is completely and fundamentally random. Before it decays, the atom exists in a superposition of decayed and not decayed. The universe, at its core, does not deal in certainties. It deals in probabilities. The math of quantum mechanics does not tell us where a particle is. It tells us the probability of finding it in a given place if we look. Reality is not a collection of solid objects with definite properties. It is a quiet, dynamic dance of probability waves. Things only become definite in the moment of interaction. This randomness is not believed to be a sign of an incomplete theory. It seems to be a genuine feature of the universe. This is the universal rule. The fabric of existence is woven from threads of uncertainty and probability. The classical world of solid objects and predictable paths is an illusion of scale. This leads to a large question. If the world is so uncertain at its foundation, why does it look so solid and dependable to us? We've explored some quiet and deep ideas from science, seeing how the universe operates on principles of uncertainty and probability. If this kind of calm exploration helps you see the world in a different way, consider liking the video and subscribing to the channel for more journeys into science and what it means. And wherever you are right now, I'm always curious to read your thoughts in the comments. Does the idea of a probabilistic universe feel unsettling, or does it offer a kind of freedom? The misconception and the bridge to our world. There is a common misunderstanding of the uncertainty principle. The story often goes that to see an electron, you have to hit it with a photon of light, and that act of measuring its position knocks it off course, changing its momentum. While this observer effect is real, it is not the true source of quantum uncertainty. It is a helpful analogy, but it misses the deeper point. The uncertainty is not caused by our measurement. The particle itself does not have a definite position and momentum before we measure it. The fuzziness is an inherent property of its wave-like nature. The reality itself is indefinite. Erwin Schrödinger, one of the pioneers of quantum theory, was troubled by this idea. To show what he saw as the strange implications of these rules, he devised his famous thought experiment in 1935, Schrödinger's cat. Imagine a cat in a sealed box. With the cat is a device with a single radioactive atom. The atom is in a quantum superposition. It has a 50% chance of decaying within an hour. If the atom decays, it triggers a mechanism that releases a poison, which would kill the cat. According to quantum mechanics, as long as the box is closed, the atom is in a superposition of both decayed and not decayed. Because the cat's fate is linked to the atom, the cat, too, must be in a superposition. It is not alive or dead. It is, in a sense, both alive and dead at the same time. Only when we open the box to measure the system does it settle into one definite state. The cat is either alive or dead. Schrödinger meant this as a paradox, to show that the quantum rules must be incomplete. A cat, in our experience, cannot be both alive and dead. But the experiment highlights the central mystery. If the quantum world is governed by superposition, why is our everyday world governed by definite states? Where is the line between them? The modern answer, the bridge between the fuzzy quantum world and our solid reality, is a process called quantum decoherence. Decoherence is the key to why we do not see things like Schrödinger's cat. The thought experiment imagines a perfectly isolated system. But in reality, perfect isolation is impossible. A large object like a cat, or even a dust mote, is a vast collection of trillions of atoms. It is constantly interacting with its environment. Air molecules bounce off it. photons of light strike it. It radiates heat. Each of these tiny interactions is a form of measurement. When a quantum system in a superposition interacts with its environment, information about its state leaks out and becomes entangled with the surrounding particles. The delicate quantum state is disrupted. Imagine dropping a pebble into a still pond, creating a perfect circular wave. Now, imagine it begins to rain, and thousands of tiny raindrops hit the surface. The original, perfect wave is quickly broken up and lost in the noise. This is what decoherence does. The environment is constantly measuring a macroscopic object at an incredible rate. The superposition of a bowling ball being in two places at once would decohere in a fraction of a nanosecond, far too fast to ever perceive. The interactions force the object to choose a single, definite, classical state. The system settles not because a person opened a box, but because it cannot maintain its fragile quantum nature against the constant influence of the outside world. So, decoherence does not eliminate the underlying quantum nature of things. It just explains why we do not see it on our scale. The universe is still fundamentally quantum and probabilistic. But for large objects, the possibilities decohere so quickly that they behave like classical objects with definite properties. Our perception of a solid, certain world is an emergent property. It is a consequence of being large systems in a vast, noisy environment. This means the classical world we experience is not the fundamental reality. It is a slice of the vast quantum reality that has been selected by decoherence. It is like a radio tuned to one station. All the other stations, the other quantum possibilities, are still there, but our receiver only picks up the one that is stable. This understanding resolves Schrödinger's paradox. The cat is never really both alive and dead for any meaningful amount of time, because it is far too large and complex to maintain a superposition. But in finding this answer, we find a deeper truth. Certainty is not the default state of the universe. It is a special case, an illusion created by scale and interaction. The default state is a quiet, limitless sea of possibility. The philosophical solution: embracing the probabilistic life. So, the universe is not a clockwork machine. It is a vast cloud of probabilities. Certainty, at the deepest level, is a myth. For the part of our brain that wants control, this can sound unsettling. If nothing is certain, what can we hold on to? If reality is a game of chance, what is the point of making plans? But perhaps we have been looking at it the wrong way. Perhaps this fundamental uncertainty is not a flaw, but the very thing that makes freedom, creativity, and growth possible. This is where science can inform a new way of living. For centuries, philosophers have debated free will versus determinism. If the universe is a deterministic clockwork, then every action you take was predetermined by a chain of events starting at the beginning of time. Your feeling of choice would be an illusion. Quantum mechanics, with its built-in indeterminism, changes this picture. The future is not written. At the subatomic level, there are real forks in the road where the outcome is not predetermined. The debate over how this quantum randomness translates to human consciousness is not settled. But it opens a door. It tells us the universe is not a closed system on a fixed track. It is an open system, creating itself in the present. The future is a landscape of probabilities, not a single destination. Think about creativity. New ideas rarely come from a logical, step-by-step process. True innovation often comes from an intuitive leap, a sudden connection that seems to emerge from nowhere. This mirrors the quantum world. It is about exploring a superposition of possibilities, and then allowing a single, new creation to emerge. A mind that demands certainty can often only produce what is already known. A mind that is comfortable with ambiguity is a mind where new ideas can grow. This can also change how we approach decisions. We often search for the perfect choice, the one with a guaranteed positive outcome. We get stuck, fearing we will make the wrong move. But if the universe itself operates on probabilities, then there is no such thing as a guaranteed outcome. Every choice is a step into a probabilistic future. This does not mean we should be careless. It means we can shift our focus from trying to predict the future to building our capacity to respond to whatever future comes. Instead of asking, "What is the one right path?" we can ask, "Which choice will make me more resilient and adaptable?" It is a shift from seeking certainty to cultivating inner strength. It frees us from the impossible task of being fortune tellers and allows us to be explorers. Perhaps the deepest impact is on our emotional well-being. Much of our anxiety comes from resisting uncertainty. We create rigid expectations for how our lives should go, and we feel pain when reality does not match our plan. We cling to beliefs and feel threatened when they are challenged. We fight against the natural flow of life. Accepting the probabilistic nature of the universe offers a path toward what some spiritual traditions call non-attachment. This is not about being passive. It is about recognizing that the only thing we truly control is our own inner state, our intentions and our responses. The outcome is never entirely in our hands. By embracing this, we can let go of the need to control every detail. We can loosen our grip. When a plan does not work out, it is not a personal failure to predict the future. It is simply one possibility emerging from a sea of others. This perspective invites us to live more fully in the present moment. The past is fixed. The future is a cloud of possibilities. The only place where we can act is in the present, the point where possibility becomes reality. The myth of certainty suggests we are unsafe until we have everything figured out. The truth of a probabilistic universe suggests that security is not found in a fixed external world, but in our own internal adaptability. It is the difference between building a fortress on what we think is solid ground, and learning to sail on an ever-changing sea. The sailor does not demand the ocean be still. The sailor learns to navigate, to read the winds and the currents, and finds freedom not in controlling the ocean, but in dancing with it. Conclusion. A new perspective on being. We began with a very human feeling, the deep and anxious need for 100% certainty. We looked for it in our plans, our beliefs, and our relationships, thinking that if we found it, we would finally feel safe. Then, we journeyed into the heart of science. We found that the universe, at its most fundamental level, has a core principle that forbids this certainty. The Heisenberg uncertainty principle showed us that reality is not made of solid, definite things, but of quiet, probabilistic waves. We learned that the solid, predictable world we experience is an illusion of scale, born from a constant, chaotic dance of decoherence. At first, this can feel unsettling. If the ground is not solid, what do we stand on? If the future is not knowable, how can we move forward? But we have also discovered a different way to see it. The search for certainty can be a cage. It can trap us in a state of fear, always worried about making the wrong move. It can make us rigid and closed off to the possibilities of the unknown. The truth of uncertainty, on the other hand, is a key that can set us free. If the universe is probabilistic, then there is no single, right, path we are meant to find. There are many paths, and every choice is a quiet, creative act that brings one of those possibilities into being. Our lives are not about finding a pre-written story, but about participating in the unfolding of the universe, moment by moment. If the future is unknowable, then we are free from the burden of trying to predict it. We can instead invest our energy in becoming the kind of people who can navigate whatever future arrives. We can cultivate resilience, curiosity, and courage. Science gives us more than technology. It gives us new metaphors for living. For a long time, we lived with the metaphor of a clockwork universe, and we tried to become predictable and efficient. Today, quantum physics offers us a new metaphor. The universe as a quiet, shimmering ocean of potential. In this universe, certainty is not the goal. Understanding is. The goal is not to have all the answers, but to ask better questions. The goal is not to eliminate doubt, but to trust in our ability to navigate it. So the next time you feel the need to be 100% certain, remember the fundamental rule of the universe. Take a breath. Let go of the illusion of control. The world is not a problem to be solved, it is a mystery to be lived. And in the heart of that mystery, in the quiet, probabilistic dance of existence, we find not the terror of chaos, but the deep and gentle freedom to be.